Cool. All right. Well, it's 6:04. We can start. Nick, I take it you can hear me, right? Cool. All right, guys. So first of all, welcome to all 92 that came out. We appreciate the support. We put these on just because we found them very helpful when we were students, and we just wanted to carry on tradition when we became TAs. So we hope you guys find this useful. Yeah, it'll be very similar to the last one. Kind of a quick little lecture overview sort of thing, and then we'll do examples. We do want to point out that we received you guys' feedback from last time and have made some changes. So first things first, we have all been trying to run through this a little slower. So that's one thing we saw most often, was that we were just trying to speed run through these things. And so we apologize for that. It's hard for us to gauge audience understanding when we can't see anybody's face. So if we're going too fast or you didn't get a chance to write something down, please feel free to unmute yourself or say something in the chat to tell us to stop or slow down. We have no problems with this whatsoever. We just don't know how people are feeling, right? So please do that for us if you're feeling overwhelmed in things, but we're going to try to go slower this time. And then second, we tried to include some more examples in the slides for you. That was another big complaint. We thought what we had was a good balance of examples, given the fact that you have so many present on Kappa, and there's only so many that we can find. But we did add a little bit more in there for you just to see you guys get those worked out for you. So that's what we have implemented for this time. But like last time, we'll have an exit poll again, so you guys can tell us what you would like improved for next time. Other than that, I'm going to do the same thing we did last time by putting a question poll, or a question topic poll rather. So you guys feel free to fill this out while you're listening. We just want to know what type of questions people want to see most, because otherwise we would be wasting your time with questions nobody wants to see. So that'll pop in the chat here in just a second while I find the link. But other than that, I will pass it off to Kate, I believe, and we'll go ahead and get started. So once again, feel free to unmute yourself. If you have a question, if you want to slow down, please don't sit there and suffer in silence. But sorry, go ahead, Kate.
Oh no, I was gonna let you finish. It's all good. First things first, can everyone see this?
I can see it, Kate, you're good.
All right, cool. So, like we said, we're just gonna go directly into this. Make sure that if anything's going too fast, just let us know and we'll make sure to slow it down so that we're all on the same page, okay? So to begin with, kind of getting into the introductory here into circuits, essentially the main difference here is that rather than dealing with something that is static, like what we were dealing with in block 1, we're dealing with things that have some movement, some components wherever we actually have charges going out through a circuit. So in case you didn't think that block 1 was exciting enough, therefore we've moved into block 2 wherever we can have a little bit more dynamics going on. And so the first thing, and one of the primary ideas that is behind everything that we're doing in circuits, is that we're going to have moving charges as defined by current. And so as you can see mathematically, this is showing that we can have a change in the amount of charge measured in coulombs for a change in time, which we measure in seconds. And this provides us the kind of essential units of current, in which we measure in amps. And this is essentially how we represent our charge current going through our circuits, the things that we've been dealing with for the last few weeks. And so a little bit of a confusion whenever you're first learning about circuits, but something that whenever you deal with them, it becomes a little bit more inherent and you kind of get an idea of what's going on. In practice, the negatively charged electrons move in the opposite direction from what we indicate as the electrical current. And so that can be represented here. You can see how the current indicated as I moves in a clockwise fashion around the circuit. However, if we're actually thinking about this in terms of how it's defined, we'll have electron flow in the opposite direction to this. I'm seeing quite a few things in the chat. I'll just make sure that that's all good. All right.
You're good, Kate. I just sent the wrong link. You're good.
Okay. I got nervous, man. I saw 12 of them up there. All right. And so going into somewhat of a worked example now, what we have here is essentially a current that changes with respect to time. So what we can see is at the very initial point, time being equivalent to 0, we have an initial current that is equivalent to 2.2 amps. And then as we progress through time, it slowly approaches what we have as 0 in currents. And so essentially this is something that we might see for something like a capacitor, whether it's charging or discharging. Essentially this can give us representation of how that current changes for a circuit. And so what we want to do in this is now solve for how many units of charge in coulombs go through this point in the wire using how we've defined current here. And so essentially all this is going to do is we're going to do some basic calculus in order to solve for Q, provided the equation that we have stating our definition of current overall. And so quite simply, you can just rearrange that equation and solve for dq. And then by integrating, we can then solve for Q as the total amount of charge that is passed through. And so kind of a key point about this is that whenever we're dealing with things like, let's say, capacitors, we're going to want to look at a time frame that goes from 0 to infinity. Essentially, it's going to be encapsulating all time, since we're trying to find the total amount of charge that's passed through the circuit. And so I've kind of already alluded to it, but one of the physical examples that can happen with such current is something like a capacitor. That can happen whenever we have it charging or discharging. So if you think back to our studio example, just last week, whenever we were doing all those things, wherever we had a capacitor that we would attach to our DC power supply, what would end up happening is that you would see that if you're watching it, your current would start at some value and then go to 0 as you were having a fully charged capacitor, right? So that's kind of a physical example of what we're indicating here. All right, and so getting into the mathematics behind this, we're just applying what we showed 2 slides ago, but like I said, we're going to be integrating from 0 to infinity so that we're encapsulating all time. Just representing that equation for current there. So essentially, whenever you do the integration, you'll see that we have a -2 as the coefficient out front. Taking that from the bounds of infinity to 0, we get 0 for plugging in infinity, and -2 as what comes out for our bottom bound. That will, of course, be negative as it is our bottom bound. And so therefore, we see that we have 2 in units of seconds being multiplied times our initial current, which we had as 2.2 amps. And so thinking back to that relation of how we define current, current is defined as coulombs per second. So if we were to multiply this times the time that we get from our integration of 2 seconds, we get our final units in terms of coulombs, and that's just going to be the total amount of charge that we get across all time here. All right, any questions about that, or do we feel good? Cool. All right. Another definition of current, and one that's not as quite as apparent, but it's good to know, is what we have here that is essentially relating to drift velocity and a few other constants that we can have associated with a wire. And so here, essentially just kind of going through each of the variables. N is defining the density of the charge carriers, and that essentially just tells you how many charge particles you have for some volume or area. And so then the next portion would be that cross-sectional area. So if we're looking at this as just a horizontal wire, that would be the circular cross-sectional area that is associated with the wire itself. The drift velocity is indicated by V with the subscript D, and then Q is just the charge of each of the charge particles that's moving through the wire. And so in this instance, we'll be using electrons. And so what you can see here is that you can just substitute in for Q, the fundamental charge of an electron. And finally, another thing that we'll kind of see a little bit more as we progress into block 3 is that we can find the current per unit area as defined by J. And so just by simply moving over that cross-sectional area and dividing our current on the left-hand side by that, we can get a representation for what J is. All right, so we've talked about current, but it's good to understand what is kind of the driving force behind it. And so how we represent that is through voltage. And so as what you can see here, voltage is defined by the amount of energy per unit of charge. And so this kind of comes and takes us back to some of the things that we learned in electrostatics. As you can see that a change in energy can be represented by a change in potential multiplied times the actual charge associated with whatever charged object we're looking at. And so this is really what drives our charges and how they move throughout our circuit. And as Nick has so well put here, in the case of something like a battery, that is caused by the chemical reaction that takes place inside of the battery itself. And so kind of the big takeaway here is that voltage is what allows us to see a lot of what we've talked about previously in terms of current. And now moving into some of the more quantitative assessments in circuits, we can see that we can calculate resistivity and resistance as indicated here. And on the left-hand side, we can see a case in which we would have a constant resistivity. And on the right-hand side, and what you'll probably see more often, is that of a differential resistivity, in which you'll have differing amounts of resistance depending on how far along some axis you are. So in the example that we're about to see, we're going to have increasing or changing resistance as we move down our x-axis. Yeah, so this equation, it was kind of early on in circuits, so it may have been a little while since we've seen it, but hopefully as we go through the as the problem statement, we'll hit a few things that'll remind you of what's going on. But the kind of key takeaway here is that we can solve for the total amount of resistance using resistivity and some of the geometric constants and parameters that we have listed here.
Can I interject real quick?
Go for it.
Yeah, there's some questions about that goofy letter that's in front of the L. That is a rho. And I just made it like a squiggly rho because there's already something rho in electromagnetism, which is charge density or volume charge density from block 1. So I just put it there to distinguish it, but it is rho, yeah.
Yeah, and just another thing to point out that has units of ohms times meters, okay? Okay. Can we please make sure that we're all muted? Yeah, and like Tyler's pointing out, that formula is also on your equation sheet as well. So moving into a worked example of this nice equation, we have here kind of a goofy shape, one that represents or can be represented as somewhat of a lampshade that is solid, right? And so essentially we start at this smaller cross-sectional area that has a radius of a divided by 2. And then we kind of siphon out until we get to a radius of a. Another kind of key thing here is that we've given this cone a resistivity represented by rho, and that's how we'll represent that resistivity as we progress through the problem. All right, and so this is simply just saying that we'll apply the equation that we saw previously in order to solve this. And so we'll kind of see how each of these things will be represented to the problem. And so kind of a question for you guys right now, for the DL, and I'll go ahead and move on to this next portion. We saw that we had leads coming both in and out of the back and the front here. So it's essentially, like I said, going from that smaller cross-sectional area to the larger one. And so a key thing to keep in mind is that we want the DL to be in the direction that our current is actually flowing. And so if you think about it that way, we would be moving along in the direction of dx, right? So our differential length is provided as dx in this problem statement because that is in the direction that our current will be flowing through the shape. All right. And so kind of another way to represent this is thinking about the cross-sectional area that the current will see or what it will be progressing through as it goes across the shape. And so what we can represent there is just taking consecutive slices of this object perpendicular to how the current is actually progressing through the object. And so there was a question for, I think it was one of the homeworks, where we had a cylinder in which the leads were coming from the inside of the cylinder to the outside, and you had to make sure to use surface area as actually the area that you were using there, because that would be the one that was perpendicular to the flow of the current through the object. So just keep in mind that you want it to be perpendicular to the flow of current, and so in this case that would be our cross-sectional area that we can represent by pi r squared. All right, so now getting into some of the math for this. And I'll leave this up for a little while so that everyone can take a look at it. what we're trying to do now is represent how R can be expressed as we move along the x-axis. And so one of the ways that we can do that is essentially what Nick has provided here is a representation that begins at a divided by 2. So essentially think of that as an intercept for our radius, if we're thinking about radius as something that depends on how far we are down the x-axis. And then we can see that we're multiplying some amount of change times x, right? And so essentially all we did to get this is that we saw that the change from our radius at the beginning to the end is equivalent to a divided by 2, right? So we're going from a divided by 2 to a. We're just going to be increasing by the amount a divided by 2 as well. And we'll be taking that essential rise and dividing it by our amount that we're moving along the x-axis, indicated by h. So that's essentially providing us the slope that's going to be representing how much subsequent rise we get for our radius, dependent on how far down the x-axis we have progressed. And then Nick also quite nicely put this into a form that we can just simply multiply times our pi in order to get the cross-sectional area as we progress through. And so now taking this back to our original equation, what we'll see here is that we can set up our differential resistivity equation and plug in things like, and I'll go ahead and annotate this because this would be equivalent to rho dl divided by a, right? And so all those things are apparent here. We have the rho as indicated by what Nick has here. Our dl will be represented by dx.
Resistor, wow.
All right. And then quite simply, the area equation that we had previously has been re-represented here. And a key thing to keep in mind is because we are going in the x direction, because we are going in the x direction, our bounds will be from 0 to h, essentially the beginning of the object until the end of it in that x direction. And then following through with all the mathematics here, we can simply see that it comes out to be the expression at the bottom of 2 times h times rho over pi a squared. I heard a little bit of stuff in the chat there. Is there any questions about this problem or anything that I can touch on again?
For the equation in the integral, on the very first line you have 4h all squared, but is it supposed to be in the parentheses? Is that a mistake?
4h all squared. Sorry, it's all right if I come back here. I see what you're saying, as opposed to on the previous equation. Yes. Yeah, so I believe that that would be 4h squared there as well. And so I think you're totally right that there is a little bit of redundancy there. So yes, that would be correct. And then I think I saw another question that was something along the lines of how do you know when to integrate and when you do not? And that comes down to when essentially our resistance will be constant as we progress along this object or not. And one of the things that kind of gives me an idea that my resistance might be changing is that in our overall equation, we can see that our resistance for an object depends on the cross-sectional area that it is seeing as it progresses, right? And so since I can see that I'm starting here at a smaller cross-sectional area and moving to a larger one, I'll see that I have subsequent changes in the overall resistance. And so therefore I would want to integrate, because then I can see that there's different amounts of changes as I go along the actual object. Does that help to clarify? All right, cool. So moving forward, now we're getting into some of the things that we've been hitting a little bit more recently. And so what we can see here is we're kind of getting into resistors. And the kind of key points that we want you guys to keep in mind whenever we're dealing with resistors in series is that, first off, whenever resistors are in series, they carry the same current. And this is essentially just going to be a conservation this is applied from a conservation of charge as it's progressing, essentially saying that the amount of charge that goes in over by resistor 1 is equivalent to what will be coming out on resistor N at the end of the line as well. And so whenever we're trying to find the equivalent resistance of a series of resistors in series, all we have to do is simply add them. There's no reciprocal sums or anything like that. It's just the sum of all the resistors that are in this sequential line. However, in opposition to that, if we had something that was in parallel, our currents will not be the same. However, the voltage drop across the resistors will. And so that's essentially saying that the voltage that starts on this side, I'll say V1 to V2, has to be the same drop across each of these so that they have the same initial and final values across the resistors. And then in order to solve for the equivalent resistance for this combination of resistors, you would do the reciprocal sum. So that's just taking 1 over each of the different resistors so that we can find their total by taking the inverse of that. All right, moving forward. Ohm's law. So essentially, whenever we have nice resistors that are of constant resistance and provide us proportional increases in voltage with current, we can apply Ohm's law. This is simply saying that in order to find our change in voltage across a resistor, we can simply multiply the current that's going across that element times its resistance. And so what we kind of put here is kind of the main takeaway, that the voltage difference across a load with resistance R is proportional to the current. Essentially, if I have higher amounts of current, I'll be getting larger and larger drops in voltage as I continue to amp that up. And so now moving into power, and this is something that we can kind of directly get from our last slide because it's applying for ohmic materials. And so essentially, in order for us to solve for power, we can solve that as our amount of current being multiplied times our change in voltage as we go across something like, let's say, a resistor. And so this can be applied in many ways, as what is shown in this middle line here. There is lots of substitutions that we can do, because not only can we represent it as I times delta V, we can substitute in what delta V is from Ohm's law and then show re-representations of that as well. And then another kind of key point here is that keep in mind that power is equivalent to a change in energy over a change in time. And so we can just simply apply some integral calculus in order to solve for energy provided some power given over some time. All right. And now moving into...
Right. He's very nice. I mean, I'm sure there's going to be an extra room too, but I guess so.
I'm so sorry. Can we make sure we're muted? So now we're moving into some of the current laws that are associated with this course. And so what you guys saw in one of the initial statements that we gave you was that the amount of current going into a junction has to be equivalent to that is coming out. And so if we have something in which 3 or more wires are intersecting, the amount of current that is coming from any one of them has to be equivalent, or the amount of current coming into that junction has to be equivalent to that coming out. There's no accumulation of charge at this point, and so this is why we're saying that it's a statement of charge conservation. And further, voltage laws can also be similarly applied, but rather than necessarily just conservation, thing to keep in mind is that this is a version of energy conservation in which the amount of voltage whenever we're analyzing a closed loop should be equivalent to 0. All right. I see that I may have been progressing through those a little bit too fast, so I can go back to any that people may have missed. But for the time being, I'll slow down my pace a little bit. So yeah, this key thing here is that whenever we're applying voltage laws, that we want the sum of all our voltage elements to come out to 0. So essentially, if I had something like a battery or something along the lines with a battery with, like, let's say a resistor, the amount of voltage gain I have from that battery should be equal but opposite in sign to the voltage drop that I experience going across the resistor. All right, and now kind of getting into the basics of how to apply these laws, what you would want to do is look at a system of circuits and kind of come up with what direction you would want to apply your loops. And like you guys know, we can either go clockwise or counterclockwise. It does not matter which one you choose, but the thing to keep in mind is that you want to be consistent. You want to make sure that each of your loops are going in either the clockwise or counterclockwise fashion, and that you're keeping consistent as you do that analysis. And so as I'm going across each of these loops, I may run into things like, let's say, a battery, a capacitor, or a resistor. And each of these will have subsequent drops or gains in voltage as I go across them. And so kind of keeping this rule of thumb, if I keep in mind that if I go from the negative to the positive terminal for either a capacitor or a battery, I'll be getting positive contributions to my delta V. The kind of thing to keep in mind there is that whatever you're coming, the side that you're coming out on is going to be the sign of your voltage as you add it to your loop rule. All right. And then in opposition to that, if we have a resistor, if we go in the same direction as the current flow, so what's indicated there is the positive current flow, we'll have negative contributions of delta V. And this kind of makes sense because if I'm going in the direction of current across a resistor, I would be expecting to have a voltage drop because that is what we expect whenever we apply Ohm's law. And the final thing there is vice versa for all the above. So if you were to come out on the negative terminal of either a capacitor or a battery, you would have drops in voltage. And if you were to go in the direction of the opposite direction of the current flow indicated for a loop, you would then have an increase in voltage going across that. All right. And so now for us to kind of work through an example, applying everything that we have here, we're going to be trying to find the value of I1. And so we're provided here all of the necessary voltages and resistances for each of the elements that you see. And we're going to be applying both the junction rule and some loop rules as we go through. And so just kind of a heads up, whenever we go through this, we're going to be doing it in the clockwise direction. You guys can choose to do it in the counterclockwise direction. We should get the same answers, just that some of our signs may be different as we work through it, okay? And so I'll go ahead and progress into the next portion. This is just simply stating, sorry,
I have
go
a
ahead.
question real quick. I just want to verify that V1 and V2, the positive terminals are facing each other, just because for some reason I'm having trouble reading space, the length of those lines.
Yeah, so the lengths, so the positive ones should be the longer ones, correct, Nick?
That's right. Yeah.
And so, yeah, you're totally right that the positive for V1 and V2 are facing each other, and then the positive terminal for V3 is pointing towards the bottom of the page.
Wait, thank you.
All right. And so the first thing that we're going to apply here is going to be the junction rule, because this will be the simplest and probably the one that is always good to start with because we know that'll hold true. We have two junctions here. There's the top junction and the bottom junction, essentially a point wherever three wires come into contact, they meet and they mingle, right? And so essentially what we can say there is that the current provided by I1, I2, and I3 will all converge onto this top junction and therefore be equivalent to 0, because the sum of all of our currents should be equivalent to 0 in the end. Same thing can be said about the same thing can be said for the bottom junction, just it's going to be a little bit of a different setup that we'll show here. And so this is just representing all the things that I said on the previous slide, wherever the sum of each of them will be equivalent to 0. But for the bottom junction, it's kind of indicating that it's equivalent to all the currents leaving as opposed to all the currents entering the junction. But they really do say the same thing. And the main takeaway here is that the sum of each of them will be, the sum of all of them will be equivalent to 0. And so now we're going to work through the loop rules for each of these as well, going in the clockwise direction. And so I'll go ahead and kind of indicate that here. And so what you'll see is that this should be very consistent with some of the definitions that we gave earlier. So if I go through this left side loop, what you'll see is I come out on this positive terminal indicated by that longer line. So I have an increase in voltage going across V1, but I'm also going in the direction of current for resistor 1. So I'll have a drop in the subsequent voltage there. Same thing for V1, except for I'm coming out on the negative side. So therefore I have a drop in voltage. And then I'm going in the opposite direction of the current indicated for I2. So I'll have an increase. And all the same things apply for our second loop here on the right, just different elements that I'm running through. All right. And so what we can do now is we can simply just add these equations, and what ends up happening is that allows us to define our equation for the big loop. The reason for that, can you demonstrate what you would do if there was a capacitor in this example? I can quickly go back and do that. So in the case, let's say that there was a capacitor here, and I'm going around in the clockwise direction. I'll say that this is the positive plate and this is the negative plate. And essentially, if I were to progress around in the clockwise fashion, I would come out on the positive side here. And so I would just add the voltage for the capacitor to the loop rule that I've indicated for the right-hand side. Make sense? All right. All right. And so, like I was saying, this equation here, essentially it defines what our overall large loop is, and that's simply by just adding all of the elements that are on the outside. But whenever we add these two going in opposite directions through that middle portion, we'll see that there is cancellation of that resistor that was in the middle. And so therefore, this equation here is equivalent to that of the big loop. All right, and now we get into the fun mathematics of everything, wherever we get to set up our system and solve for all of the variables that we are trying to find here. Should the signs for IR1 and IR2 be flipped? On this one or on the following slide? Oop. My apologies. So like I said, for I1, R1, we're indicating that as negative because we're going in the direction of current, and positive because we're going against the direction of current for the left-hand side, right? And I believe that that is consistent here for our top equation. And so now all it comes down to is solving the system of equations, and that involves us solving for I2 and I3 in terms that we can represent as current 1. And so essentially all you'll have to do here is we can take the left loop equation that was provided as our first equation on the last slide and solve it so that we have I2, and it is inherently provided in the variable of I1. And then we can solve for current I3 from the right-hand loop because there's only I1 and I2 there, and substitute what we found in our previous equation back into this system. And so now taking all those equations, we can plug everything in and then do a lot of algebra in order to solve for what current 1 was. And so essentially this is taking all those elements, including resistors, voltages, and simply solving for what current 1 is by taking it all out in the end. And one of the things that I really like to endorse is that since you guys all have your own calculators, if you understand how to set up a system of equations in something like a TI, then it is actually quite simple to solve these, but it's good to be familiar with that. All right. So that's coming towards the end of my time. I'm about to pass it off to Tyler. Is there any questions about anything doing with loop rule, anything with resistors, anything in general that we could cover?
I have a quick question.
Go for it.
Will it always be the case that the outer loop will not contribute to the system of equations?
So I think that that was something that was kind of apparent for this one. The reason why we were able to do that for this was that we could fully specify a system of equations to solve for everything that we needed in the 3 equations that we were given. And so it depends on what all you need to solve is what I would say. Anything else to add to that?
Can I say something real quick?
Go for it.
Yeah, Nate, this might be with regards to your question, but you were asking about flows out of a circuit.
Yeah.
Yeah.
Sorry.
Yeah, go ahead and elaborate what you mean by that.
Oh, yeah. So I guess I was just always confused because I always thought that there had to be a flow out, because if there wasn't a current out, then it wasn't a closed circuit. So how could there be? That's what I'm a little bit confused on, because I always thought that it had to, you know, like be closed.
So that's going back to Kirchhoff's junction rule, which says that the sum of currents going into a junction is equal to the sum of currents going out of a junction. And obviously, the way I wrote it for that problem, if all the currents were positive, that wouldn't make any sense at all. Like, can you scroll up a few slides? Yeah, like if all the currents were positive and all of them were going up into that top junction, then that wouldn't make any sense at all, because we would just have charge piling up at that top junction. What I did there, or I guess what that insinuates, is that in reality, one of those currents, one or more, is going to be negative, which means that even though I drew them all going into that top junction, I just get a negative answer, which means it's actually in the opposite direction.
Okay, that makes more sense.
Yeah,
Thanks.
we're just guessing the direction of the currents, and then depending on the sign that we get from it, we'll know whether or not we guessed correctly.
I think in this problem, I1 actually did come out negative. But yeah.
Yes, it did. All right, are you ready, Tyler?
Awesome. I am, Kate. Thank you very much. Like I said, any last questions for Kate? You guys had some good questions so far, and good job, by the way, letting us know we're going too fast or not. Like I said, we have no clue if you guys don't tell us, so we appreciate that input. So thank you, guys. But all right, and it looks like people want to see another Kirchhoff question, so we can come back to that later. No worries. Caleb's got one question here. So if you have a capacitor in a circuit and it is being crossed in a loop, well, what do you put in the Kirchhoff law for the loop? Like a resistor is IR, so what is the capacitor? Oh, gotcha. It's good question. Normally when we have capacitors in these sort of Kirchhoff law type equations and loops and things like that, we normally denote it just as V sub C, right? Or V sub C1, right? The voltage in a capacitor 1 or voltage in capacitor 2, that sort of thing. But am I missing something, Nick?
Yeah, we can also do a little bit more, and we can go back to definition of capacitance and say that if C is equal to Q over delta V, and if we solve for delta V, that's Q over C,
Yeah.
I think. Yeah.
Exactly.
That way we can just get charged by itself.
Yeah, either one of those, Caleb, would work for you.
Yeah, we don't do too
Either
much.
one of those would work, but if you see in an exam question, normally they would just say assume as VC. I think is for all the exam questions I've seen. So does that answer your question? Cool. Right on. Good question. Okay, guys. So I have the pleasure of going over sorry, that would be terrible. Going over capacitors and sort of the introduction to these suckers. So I think that should start sharing my screen here. That should come up momentarily. Perfect. All right, everybody can see and hear me, I take it. Okay, so again, thank you, Kate, for giving us that introduction there, just to Ohm's law, voltages, resistors, all that good stuff. So from here, after we were kind of developed all of this knowledge in our knowledge of block 2, we went on to these objects called capacitors, right? And so again, these are these kind of cylindrical looking objects, right, that we worked with in experiments a couple of times, right? They'll have 2 leads at the top. One's usually positive and one is negative, right? And these things they basically just store charge, right? So we can think of them, if you want, if it helps, think of them as giant buckets, right? Whereas charge and electrons are like water drops or the flow of water, right? So capacitors in a circuit really are just, they start off empty, right? And we're just going to fill them as time goes on. All right, we'll deal with that a little bit more when Nick goes over RC circuits and things, but just in general, these are pretty much charge buckets, right? They're just things that we put charge into and we can take charge out of as we please, all right? So the definition of capacitance as it relates to charge and voltage is given by this equation right here, right? Where capacitance is equal to the charge it stores over the potential difference applied to its 2 electrodes, right? So there's going to be 2 electrodes there, and there's a potential difference between those 2 electrodes. And remember in this class, how we sort of draw a capacitor, right? To actually analyze it is by having two parallel plates, one with positive charges and one with negative charges. This ensures that we get an electric field between the plates, right? That flows from the top plate, which is positive, right, to the bottom plate, which is negative. Right, and keep in mind that the top doesn't always have to be positive. You just have to have opposites, right? So it doesn't really matter. I could have made this side positive down here if I wanted to, right? That would just means the electric field would flow in the opposite direction, right? So just keep in mind the electric field flows from positive to negative. So that's all we need to really take away from that. But yeah, so just right there, basic definition of capacitance, right? And kind of how we would model it. And then last thing, the units on capacitance, because units in physics are very important, are in farads, right? So similar to how charges in coulombs, these are in farads, right? It's going to be 1 coulomb per volt is what the definition of a farad is, right? So just a little bit of background there. But and one thing I do want to point out is that you guys, if you were in studio and did those in-person experiments, a farad is a really, really big unit, right? Whereas I would say a meter or a kilogram isn't that big of a unit. A farad is a large unit, right? If we have a 1 farad capacitor, that's big, right? That's a large capacitor, right? So if you're taking your exam and you're looking at a multiple choice question that asks you to solve for capacitance, I would be really surprised if it was greater, any number greater than like 10 to the minus third, for example, right? That would be a typical capacitance value, right? So just a little guess and check, but farads are pretty big units, so we should be getting a very, very small value for those. So I've talked enough about that. So I will move on here without any other questions, the way it looks like. All right, tips and tricks. Yep, cool. Perfect. All righty. So somebody mentioned it a little bit earlier in a good question they had. But one of the main equations we worked with, we were talking about capacitors, was the equation for the energy stored in a capacitor. Right. So on your equation sheet, it'll be in that block 2 section right under circuits. And the main form that it takes on your equation sheet is this form right there, right? U equals 1/2 C times the potential difference, delta V squared, right? So remember, this is how it appears on your equation sheet, but that doesn't necessarily mean that's the only form we have to work with, right? So, and for example, you're given charge and capacitance, for example, right? Then you can't use this expression here, right? That's not going to work because I don't know how voltage changes. Right, so making that, noticing that, I could go down back to my original capacitance expression, right, and rearrange this any way I want, right? I could say Q equals CV, or like Nick has written here, delta V equals Q over C, right? Any one of those 3 forms is valid, right? Entirely valid for me, right? And then using this relationship right here, I can plug in any one of these variables for any other variable back into my energy expression, right? So very, very similar again to the Ohm's law and power calculations we had earlier, right? Because I know this, then P equals IV can take many different forms, right? So basically the same story, right? But keep in mind that there's a 1/2 and a squared involved, right? So there's a little more involved, right? But keep in mind that we can use the same strategies. We can make the same substitutions, right? And any one of those equations is valid. I just have to know what happens to all of the variables that are in my equation for me to use those variables, right? So I don't think that if I don't know how voltage changes, well, then I can't have it in my equation. All right, I see a question here. The bottom equation, shouldn't it be U equals 1/2 C? Yep, yes, it should be, right there. U equals 1/2 Q squared over C. Thank you, I appreciate that. Very good point there, cool. So yeah, so just to add on the last one, right? So we could have U equals 1/2 CV squared, equals 1/2 Q squared over C, or U equals 1/2 QV, right? Any one of those expressions will work out just fine, right? Or sorry, that should be, if I plug in C there, be 1/2. Yeah, I had it, cool. All right. Cool. All right. So that's yeah, okay, good question, Lisa. So U equals QV, that's more of a unit topic 1 expression. She's talking about this one right here, guys, where U is, or the change in potential is equal to Q times the change in potential. So potential energy is the change in voltage over there. That's an equation we don't work with too often in Unit 2. It's inherently useful because everything in physics is inherently useful, right? But it's not really going to get us anywhere in this unit specifically, right? You're going to be using more often than not, you're going to be using something that looks like this. All right. So I'm sorry, that took a second to update. A little bit of lag here, but yeah, this equation we covered more in Unit 1, and it deals with the energy of like point charges, that sort of thing, right? So this isn't going to be inherently useful in Block 2. Right, but good thing to hold on to, and you can manipulate it technically, but we don't expect that from you. Normally, we are just looking for this expression right here. Cool. All right. So moving on. Right. So similar to the way we had resistors and batteries and things like that in Kate's section, right? We can now do the same thing with capacitors. Right. We can have capacitors in series and capacitors in parallel. Right. It's important to remember what is the same for things in series and what is the same for things in parallel, right? So if I have resistors here, so if I have resistors, right, current is the same in series. Current is the same, right? So this means that every resistor that's in series with one another, those will all see the same current, right? And really that boils down to if something comes into my resistor, that same amount must come out of my resistor. Right, so kind of like pipes, right, in the flow of water. Whatever I put into a pipe has to come out of the pipe on the other end. So that's kind of the logic behind that, right? And then for both, same in, I should put in series here, right? So, and then I will write for resistors and capacitors alike, right? For both of these two, voltage is the same in parallel, right? So resistors and capacitors, voltage, same in parallel, right? So that's kind of nice, right? No matter what circuit configuration we're dealing with, as in if I have resistors or capacitors, right? If they're in parallel, then they're always going to see the same voltage, right? No matter what I'm dealing with there. It could be, like I said, resistors, capacitors, anything, right? Those things are always going to see the same voltage in parallel, right? And then obviously the last one here, I didn't leave myself too much room, but capacitors in series, right? They have the same charge, right? So, so charge is the same in series. Right, so similar to resistors, right, where resistors what's the same for resistors in series is current. Sorry, charge is the same for capacitors in series, right? So remember, current is the flow of charges, right? So kind of similar topics, right? But remember that charge is the same in series. So we're running out of room here. Series, perfect. Cool. All right, so now we've covered basically what's the same and what's different, right? That's usually more helpful for experiments and things like that. But in case you're asked about some theory or something like that on the exam, just want to cover that. But what is important to remember about analyzing these two is that they differ in how we add them up equivalently, right? So remember, resistors in series, I could just add them straight up, right? So for series, right, our equivalent was just the sum of all resistor values, right? Just adding them all straight up, right? Nothing fancy there, just adding them all straight up, right? For capacitors in series, right? C equivalent, right? You're going to do what you did for resistors in parallel, right? So it's that 1/, right? The sum of the inverses, that sort of thing, right? So I forget exactly how to write it here, but it should be C to the -1, all that, -1. All right, so again, so like I said, adding them up like we would resistors in parallel, right? Just remember those are backwards from one another. All right, got a question here. What do they look like when they're in parallel? Are you talking about capacitors, Adriana? I take it. Cool. All right. And so you asked, what do they look like? So that can mean a couple of things. As far as like the actual picture, I would be shocked if you were talking about this, but obviously they look like that, like they're in parallel. All right, but if you're talking about how to add them up in parallel, then you're just going to add them straight up, right? So for C in, I'll do C sub P for parallel, right? You're going to get just the addition, right? Just the sum of all of our capacitors here, right? So 1 and 2 or whatever, right? So for parallel, our life is pretty easy when it comes to capacitors, right? We're just going to add them straight up, right? But remember, in series, it's the 1/, relationship. It's like we did resistors in parallel, right? So as long as you can remember the resistor rules, all you have to do is flip those, right? I'm making it sound more complicated than it needs to be. I apologize, but if you remember resistor rules, just flip them, right? They're just flip them. They're exactly opposite of one another. right? So yep, Nick has a good representation of what that looks like, right? So that's what that formula will look like. I got one more question here. What would happen to current of capacitors in series? So that's a good point. So remember, current is the flow of charges. So we can't make the same argument and say that current is the same for capacitors in series, right? Because that's not inherently true, right? We have charge is the same for capacitors in series because charge piles up on our capacitor plates, right? So I have, let's say my battery was up here, right? I got my battery up there. So that means current's flowing this way, right? So that means I'm going to have some pile up of charges here, right? Which forces the negatives to go there, and then so on and so forth, right? I'll get that same thing, right? Because I know if I started with some amount of charge up here, I've got Q equals, I don't know, let's say 10 coulombs or whatever, right? I can't lose any, right? Anywhere in between these two, right? Then as in like, I can't just like completely destroy some charge, right? It's got to go somewhere, but I'll end up with 10 coulombs here at the end, right? All these have got to be the same charge because of the way the capacitors work, right? It's kind of sort of a staggered thing, right? So whatever charge comes on the first one, right, has to leave that first one and go to the second one, so on and so forth. Does that answer your question there? Yeah, what's up, Nick?
Okay, I just got a little confused because I thought that charge that flowed through the capacitor can only be AC unless if it like bridged it and arced or something weird, right?
Let's see. So you're talking about, sorry, Nate, say that one more time. Sorry, you kind of cut it a little bit for me.
Oh yeah. So so I was just making sure that actually have like your flow of charges, for that to actually go through the capacitor, doesn't it have to be an AC current to do that? To actually have a flow on the other side?
Unless I'm mistaken, which I'm not, I'm obviously not a phys major. You can capacitors work with both DC and AC power supplies, as in in studio, right? That box that you hook up your circuits to, that's a DC power supply. Granted, it's plugged into a wall, right? So it's supplied with AC power, but it provides DC power, right? So for capacitors, it doesn't matter what type of current flow you've got. It could be DC or AC, right? They'll work either way. Does that make sense? There's different rules, but they'll work either way.
Yeah, that sounds good. Thank you.
Can I add to that real quick?
Yeah, and don't you worry, we'll get to AC circuits in a few minutes, so no worries.
That's just what I was about to say. Well, there's more on that later.
Cool. Yeah, completely different set of rules, and it'll tell you if the circuit it'll either tell you straight up if the circuit is AC, or it will give you the current function, and if the current function is a sine wave, right, then you know it's an AC function, right? So it'll be pretty obvious which set of rules you're supposed to use, right? So, all right, Alex Chavez. So does the charge only flow on the plates? So that's a good question. So yeah, remember that a capacitor is really just two plates, right, with nothing but empty space in between, right? So I don't have things that are flowing in between these two plates here, right? So I don't want to say that they only flow on the plates, but they stack up on the plates is the phrase I would use. Does that make sense, Alex? Sorry. They will stagger here, and then that will make negative charges go there. Cool. Awesome. Thank you. Good question. Good question, right? Remember, we can't have anything flow in between here because there's just nothing but air, right? Even if we had a dielectric, that's not how it works, right? Nothing flows in between those two plates. Good question. All right, so I'm lagging behind a little bit here, so I'm going to speed up just a hair. But good news is we've already covered most of this, so it's okay. I tend to talk too much at the start, so that's all right. But first thing we've got here after series, right, is capacitors in parallel, right? So I kind of covered this already, but just like resistors in series, capacitors in parallel will be added up to each other just straight up. No fancy rules here, right? Just add them all together. Right, so just remember, these rules are opposite of resistors, right? So as long as you remember one, you've got the other, right? Just remember they are opposites of one another, right? If you try to analyze capacitors in parallel doing the 1/over thing, right? That will not get you the right answer, okay? So just remember, opposite of resistors. And that's all I've got to say about that. Okay, so next we have, we're this example is deriving the capacitance of a parallel plate capacitor, as in we're getting to basically how we got to this formula here. It's a good example. I think it's just a little bit out, excuse me, outside of your, I guess, outside of your knowledge, as in you don't need to know how to derive this equation specifically, but the steps are good for figuring out really how to find the capacitance between two objects, right? Which is very applicable. So I'll go through it real quick, and there's another example after this that deals with more specific, like capacitance between two objects sort of thing. So, so whenever we are trying to find capacitance, and as in deriving it, right, which you might have to do for your free response question, that's usually a pretty popular one, right? Gauss's law doesn't go away, unfortunately, right? Anytime we have electric fields, right? So in this case, if my line would correct here, anytime we've got electric fields present, right, where we do in between two capacitor plates, right, Gauss's law applies, right? So I've got an E field between those two, right? And then I can go from there. So where we start here is the E field made by an infinite sheet. Okay, and that's what this formula is right here, right? And so normally we like to avoid using the word infinite, or they like to use the avoid using the word infinite on an exam because it's a dead giveaway. They will usually say like a very large sheet of charge, or maybe this can be approximated by an infinite sheet, maybe, right? But keep in mind there's different words to describe basically how to get to this formula, right? But that is the formula made by an infinite sheet of charge, and that's what we approximate these two to be, right? Two infinite sheets where we have charge stored on them. All right, so that's where we would start. We were actually going through and deriving this thing. So I'd start with that formula there, right? But we have two plates, so I will multiply that by 2, and to get the total E field in between those two capacitor plates to be sigma over epsilon naught. Okay, that's what that would end up being just from the E field perspective, right? We had a little bit, we have to go from E field to voltage and then to capacitance, but this is the first step, right? We got to make sure we get that E field calculation correct, right? Just so we can start at the race, right? Notice we didn't use Gauss's law for this specific example because this formula is given to us on the equation sheet, right? But if you have two concentric spheres that store charge or something like that, right, then you will have to use Gauss's law to find all this stuff in between here, right? So we'll get to that in a few minutes, but that's kind of what the basis where Gauss's law is coming from in this unit. So remember we had sigma over epsilon naught from the last slide, right? So now we're going to work with that. We're going to pick apart what sigma is, right? So I would be surprised if all of you remembered, but sigma from unit 1 is a 2-dimensional charge density, right? It's the charge density of a 2-dimensional object, in this case, our infinite sheet, okay? That's going to be our charge per unit area, right? Again, because it's 2-dimensional. So we'll rearrange that just to get Q over epsilon naught A, okay? So at this point, I've completely simplified my E field expression. I'm good to go, right? I got nothing else to worry about. I can just go from here and plug it into my voltage expression. So one we've been working with a lot in unit 2 is this integral expression here, right? Where delta V is the integral of E field dotted with the differential length vector, right? In colloquial terms, it's really just over what distance the E field flows. And in this case, in most cases for capacitors, we're just going to have a distance D that separates the two plates, right? So between these two plates here is just distance D. Right. So more often than not, that's what it's going to turn into. But just remember, it's the direction in which the E field flows, right? That is what your DL is going to end up being, okay? So I will plug in my Q over epsilon naught A, right, for E field right there, right? And then I'll just integrate it, right, with respect to that differential length, right? But notice that our E field is constant between two plates, right? So I can make some fancy integrating tools, right? I can pull that out of my integral. So really, I'm just getting E integral DL, right, which is just going to be E times L or E times D there. Okay, and that's covered on the next slide, but I just wanted to give that intro. Excuse me. How's my speed looking? Is that everybody still with me here? That makes sense? If I don't hear anything, I'll just assume that's good. Cool, thank you. Appreciate it, Lisa. All right, so moving on from there, right, exactly what I said. So we're just going to get going to pull that E field out of our integral here, right? So that's E, and then I will just multiply it by the distance D that I got, okay? And I'll end up with QD over epsilon naught A. That is equal to my voltage, right? Whoops, delta V, QD over epsilon naught A, right? And so one of the most important things to remember about these types of problems is that you're not done yet, right? Just because we solve for delta V doesn't mean our problem is over, right? Remember, the problem asked us for capacitance, right? Not for voltage, but for capacitance, right? The good news is you've already done 98% of the work, as in all you have to do is plug in that voltage expression right there, right? And really all that does is flip the entire thing around and get rid of the Q, right? Because we don't know what the charge actually is, so it can't appear in my capacitance expression at all, right? So I've got Q over QD over epsilon naught A, right? And I will get epsilon naught A over D, right? Sophia's got a good question here. Why is it absolute value again? If you're talking about this term right here, it's because the capacitance value can never be negative, right? A capacitor is a physical object, right? So I can't say, I would never say that a bucket has negative bucketness, right? That it stores -8 gallons, right? That just doesn't make any sense, right? So whenever we're talking about the voltage in a capacitor, it's always going to be absolute value. Does that make sense?
God.
Cool, thank you. All right, Lisa, technically we are given this equation, right? If you're talking about epsilon naught A over D, absolutely, yes, you are given that equation. It is at the bottom of your equation sheet, I believe, or maybe not. Maybe that's one of that they decided to put in the block 2 section. I don't know, but it is on your equation sheet. I promise you that. I know it is. Just don't know the exact location. Okay, cool. All right, so like I said, that one, I would be surprised if you were asked to derive that specifically, but its general process is going to be the same as the other examples that you might be, used to doing, right? So it's important, but remembering that verbatim isn't necessarily required, right? So we'll move on from that. So holy cow, I gotta speed up here. Sorry, Nick. But okay. So next big topic with capacitors we talked about was the introduction of what we call a dielectric, right? And more often than not, these dielectrics are they take the form of like nylon or Kevlar, things like that, right? That are blocks of stuff that we basically just put in between our 2 capacitor plates, right? And they are represented by kappa, right? The dielectric constant, okay? Really, the main takeaway from these things is you have to realize that they increase the capacitance of our capacitor. How? We'll get into that. But in general, right, dielectrics increase the capacitance of our capacitor. Right, so what that means from a math perspective, right, is if I have this normally, epsilon naught A over D, all that changes if I introduce a dielectric is I just multiply it onto both sides. Right, technically it gets multiplied onto epsilon naught, right, which is basically how easy it is for me to push things through space. Dielectrics make that easier for us. So technically I should I should write it over here. But all right, so that's just what happens mathematically, right? But from a conceptual standpoint, I'll do a quick picture of that and we can figure out what happens there. So this picture should look familiar. It's just the opposite of what I had drawn earlier. Previously I had positives on the top, negatives on the bottom, right? This diagram is just flipped, okay? So normally this is what happens. Got my E field flowing from the positive side to the negative side, right? And then I will have my dielectric that I'll insert, right in between those 2 plates. Right, so that's shown on this next slide here. Right, so when I increase this dielectric, what ends up happening, right, is we call it polarization, right? And really all that means is that the charges present in the dielectric, so these suckers right here, these oval looking things, right, will reorient themselves such that you have the positives all on one side and the negatives all on the other side. Okay, so notice how all of these positives are lined up, right? And all of these negatives are lined up, okay? What this result then, notice, is that this orientation is different than the normal orientation of my capacitor. As in, if I've got positives here, well, I have negatives up here, right? So that means that the electric field created by this dielectric is in the opposite direction of my normal electric field, right? So the net result of that is that the dielectric ends up making a small electric field that opposes my original, right? So I'll name it ED for the electric field made by a dielectric, right? Remember, because positive charges make electric field lines that flow away from them. So the effect of all these little vectors here adding up just means that I've got an E field that is weak, but it's in the opposite direction of my original E field, okay? What that means for us mathematically is that my E field will decrease, like we said, right? So if E field decreases, well then by definition, delta V must decrease, right? Because they are directly related. And if delta V decreases, it is in the denominator down here, right? So if I divide by a smaller number, my result will increase, right? So really that's what happens, right? I've got an opposing electric field in the opposite direction, right? It will decrease, like I said, decrease that overall E field, which decreases the voltage stored between or stored in that capacitor, right? Which will increase the capacitance, right? And you might be asking, okay, well, what about Q, right? And the important thing to note here that Nick's already pointed out for us is the charge is fixed, right? Charge doesn't change on these suckers, right? No matter what I do to it, right? What I put a dielectric in between, it doesn't matter, right? Charge is always the same. So that's why capacitance increases, okay? Any questions about that before I move on here? Cool, I'll take that as a no. Awesome. All righty. So yeah, this is kind of a rehash of what I was saying. Basically, with dielectrics, right, I'm just going to multiply epsilon naught by the factor of kappa, right? That's just coming from Gauss's law. This is starting from Gauss's law, right? You can start wherever you would like as far as the dielectric goes, but it's just taking you back to the beginning here. All right. So this is the worked example I mentioned earlier, right, and where we're actually finding the capacitance of concentric spheres. It is 7:10, so I'll just toss it out there real quick because we have AC circuits to go through. Do you guys want me to go through this one right now? I can do it. It's not a big deal, but I just want to make sure for time purposes. Yeah, okay, got one yes. Cool. Cool. I will do that. Just want to check and make sure. Appreciate it. All right, guys. So we are dealing with here, this is, and so just as an extra incentive for you guys to pay attention, this is a good candidate for a free response question, right? Nothing is certain and we haven't seen the exam yet, but I will say these questions make good candidates for free response question, right? So it's good to know how this overall process works and then we can go from there, okay? So this is similar to this is pretty much exactly what it'll look like, right? I've got some object, in this case, a spherical shell of radius A. I know it's kind of hard to see here, but this is radius A, the inner radius. And then it's nested within a larger spherical shell of radius B, right? So sorry, that's still kind of hard to see, but it's a little better. So B is the outer radius, A is the inner radius. The space between them is filled with a dielectric with dielectric constant K, right? So remember, dielectrics are just things that we put in between our two capacitor plates, right? They can take any form we want, but they're going to go kind of in here, right? That's what this purple stuff is. Okay, so that's where my dielectric is. I'm trying to find the capacitance of this arrangement, right? That's my goal, right? And this will actually parallel a fair response question pretty well. So where do we start with this, right? It's been a long time since we've dealt with problems like this in block 2. And with these types of problems, I'm always going to start with Gauss's law, right? And you might be disappointed to hear that because you thought you were done with Gauss's law for unit 1. I know I was disappointed in it, but it's pretty important. It comes back, right? So we're going to start, like I mentioned, with Gauss's law, right? Actually, well, we're going to start with Gauss's law, but normally this is the problem as well. The problem says normally assume a charge of plus Q on the inner electrode and a charge of negative Q on the outer electrode, right? All this means for you is that really Q equals Q, right? I don't have to integrate to find DQ or do any of that garbage, right? I don't have to do that. Okay, that's the one good thing about these Gauss's law problems, that they're always more straightforward in unit 2 than they were in unit 1, right? There will be no finding of DQ, none at all. They will give you a charge on those electrodes, okay? So just assume Q equals Q and move on from there. So like Nick said here, right, if I have Q, right, well then I need voltage, right? That's the last thing I need to solve for my capacitance value, right? So all of the rest of my work will be to solve for delta V, right? That's my goal. So now we'll go back to what I was saying. So whenever we're starting these problems, we will start again with Gauss's law. Okay, we want to find the electric field between these two radii such that A less than R less than B, right? And so we will always, like I said, start with Gauss's law. Keep in mind our two symmetry arguments, right, still apply, right? That's how we're able to use Gauss's law in the first place, right? So don't forget about those. I can't remember for the life of me if this question does come up. I think they'll ask you for them, but if they do, just remember that my E field and area vectors must be parallel to each other, right? That's what that's what that 11 means, right? And then only then once that happens, my E field, if that is constant, I can pull that out of the integral. right? And that's how I can get to just E times A here, right? So symmetry arguments still apply. We just might not ask you for them, right? Just keep that in mind. Excuse me, the same explanations work, okay? E times A, that's how we simplify integral of E dot dA, okay? So I will make that assumption here first, just tossing it out there, right? So now we got EA equals Q over epsilon naught, okay? Moving on a little bit here. All right, pretty much exactly what I said, right? Except plugging in our surface area of a sphere, right? Because I've got a spherical Gaussian surface, right? In this case, in most cases, it will either be a sphere or a cylinder, right? So remember, for a cylinder, it would be 2 pi r L, right? For our surface area, right? That would be SA for surface area, okay? But you can have, it's likely that you'll get either one, right? So spherical or cylindrical, doesn't really matter, right? All that changes is the area formula right there, okay? And so notice that Nick has already included for us the dielectric constant, which is great because I kind of forgot about it myself, right? So that always just gets multiplied onto epsilon naught, right? If you have a dielectric, just slap it on there, right? Just slap on there so you don't forget about it like I did, right? It always gets multiplied onto epsilon naught, right? So what we end up with is a pretty familiar formula, except for that kappa there, right? So Q over 4 pi kappa epsilon naught r squared, right? So normally in unit 1, it would just look like E equals Q over 4 pi r squared epsilon naught, right? So pretty similar, because I just don't forget about that dielectric. All right, that's the entire point of why we're even trying to find the capacitance of this object, okay? Because we put a dielectric in there. So good news is, once I've got this electric field formula here, right, I can, whoops, sorry, I skipped a bunch of slides, that's my bad. Go back here. Gosh, sorry about that. I accidentally pressed the arrow. So I'll let that catch up for a second. Cool, okay, looks like it's there. Sorry about that. So we were right here, right? I said that the electric field is equal to Q over 4 pi kappa epsilon naught r squared. All right, so I will take that electric field formula and I will plug it into my lovely voltage expression here, right? That same voltage integral I worked with in the last problem. Okay, I'm going to integrate, like I said, with respect to a DL, right? A differential length vector, right? In this case, it's a little more ambiguous just because I don't have 2 parallel plates and I don't have a distance directly between those two, right? But you should know that electric fields, right? In this case, my electric field I'm dealing with is it moves in the radial direction, right? As an E field goes from the positive to the negative, right? So I can't remember if this one's positive or if that one's negative, either way, right? It goes from positive to negative, so that means that my DL, right, becomes a DR. All right, it moves in the radial direction. Okay, so that's what is right there, right? They got the integral from A to B, so radius A, which is here, and radius B, which is there. All right, I'm integrating to find the potential difference between my two objects, right? So I'll go through the calculus or whatever, and that's totally fine because you guys all have a calculator anyway, so really it shouldn't be too big of a deal. But I will go through and end up solving for a delta V expression that looks like this, right? For concentric spheres, right? Q over 4 pi K epsilon naught times 1 over A minus 1 over B. Right, so I see a question in the chat real quick here. Yep, so voltage is always absolute valued when applying it to capacitance. Yes, so yes, like I said, so remember, we can never have a negative capacitance value, right? Capacitance, like I said, is a physical property of this object to be able to store charge, right? It never makes sense to say that value is negative, right? That just makes no sense at all, right? That's like saying my phone is charged to negative 80%. It just, I mean, why? It doesn't make any sense, right? So it's always going to be absolute valued when we're talking about capacitance, right? Then I saw another good question. Isn't it the negative integral? Isaiah, so that's a good question as well. On your formula sheet, you're right. It looks like this right here. It's the negative integral, right, of E dot dl, right? But what they don't, or what I say they, but they didn't tell me when I was a student. They didn't tell us when we were students was that this negative sign refers to when the bounds are normally flipped, as in all the calculus that we do, normally you go from a small value to a big value. Oops, not just writing value, you go from small to big here, right? With voltage, this expression assumes that you're going from a big value to a small value, right? So that's why that negative sign is there, right? That negative sign, you can either keep it there and keep the bounds from big to small, or you can flip them and ignore the negative sign, right? That's another rule of, I believe we learned it in Calc 2. Right, you can either have the negative sign. The negative sign just flips the bounds. Sorry, I should stop talking. Right, the negative sign just flips the bounds on your integral. Right, you're allowed to do that if you want. All right, does that answer your question, Isaiah? Very good question. Very good question. Right. It's really just important to remember from this is don't do both things. Do not do this. You can't have the negative integral of something from small to big, right? That doesn't work, right? It's one or the other, right? You either keep the negative sign and make the bounds from big to small, or you get rid of the negative sign and just flip the bounds, okay? Doesn't matter how you do it, right? I personally like to get rid of the negative sign just so I don't have to deal with it later, right? But you can do it however way you want. Doesn't really matter, okay? But good questions though, right? So we got our voltage expression here, right? So I'm going to take that and plug it into my capacitance expression, right? So our C equals Q over V, okay? So similar to my original example, right, where we just had just a general capacitor with a dielectric, I'm going to plug that in for delta V here, right? And then divide or have Q divided by that to get my capacitance, right? So the beautiful thing about that is really you just get the reciprocal of what your voltage was without the charge, right? That's really what it is. Just take the reciprocal, whoops. Just took the reciprocal, right? Because we divided by that massive expression and we ended up with 4 pi K epsilon naught over 1 over A minus 1 over B. All right. So yeah, that's a pretty good example. I would not be surprised if that was a free response question, right? That's all I'm gonna say. It wouldn't surprise me. But does that make sense? So this eliminates the need for an example based on this problem as well. So it's probably a good thing we went over it. But does that make sense to everybody that wanted to see this one done? Did I miss any parts specifically or something you'd like me to go over again? I don't mind at all, but just want to make sure. Cool. All right. Nick, I'm so sorry. At this point, I will toss it off to you. I apologize. I went really, really long, but that does eliminate the need for us to do one example. So go right ahead.
You're all good. Yeah, no, like we said at the beginning, people wanted us to slow down a bit for the last one, so we did. So it's sort of just a balancing game that we'll figure out eventually. But yeah, let me pull up my my sections real quick.
Yeah, no worries. And just oops, sorry. I unmuted myself on the wrong thing. Just so you guys know, this is supposed to go till 8, but we don't mind staying afterwards if you guys have more questions, right? We're still trying to get the hang of the timing of everything. So it's not a big deal to us if we stay afterwards. So don't feel like you have to hop off at 8 right away. Still have questions, we'll be here to answer them, right? It's not a big deal, right? So just hold on to them if you have those. And then as soon as some of you are heading out as well, I will repost that exit poll just so we can get a gauge on how well we did. We would really appreciate if you guys filled that out for us. But other than that, sorry, I will finally shut up and let.
You're all good. You're all good. And one quick thing I'll say is that even though it's dark outside now, my neighbor's been doing stuff in his yard. So if it gets noisy, let me know and I will find a different location. But shoot, screen share, where is it? Right here. Copy. Screen share. Perfect. Okay, and I'll check back into the chat periodically to see what I'm missing, but I changed it. It's in here. Closed it. Oops. Shoot, my bad. Perfect. And slide 52. All right, so Tyler left off on this concentric spheres problem. So I'll just pick up where he left off and talk about topic 2E, which was all about RC circuits. And RC circuits, they come in two forms. You can either have charging RC circuits, where a capacitor would start out initially uncharged at t equals 0. And then maybe at t equals 0, we would throw the switch, we would close the switch, and then a battery or a voltage source, just something with a constant voltage source over here, would start charging the capacitor. The equation on your equation sheet for charging RC circuits is Q of t equals Q final 1 minus e to the negative t over RC. And the reason why we know it's this equation that applies to charging RC circuits and not discharging RC circuits is because, well, if we think about just the graph of 1 minus e to the negative x, let's say, if I have 1 minus e to the negative x, that's going to look like something that starts small and then rises to an asymptote value. And that's pretty much the behavior we'll see with capacitors in RC circuits. If they start out initially uncharged and we hook them up to a battery through a resistor, then if I close the switch, the charge on them is going to increase until it reaches some value where it asymptotes. And we can go through a mini derivation of how we got to this equation. It's not too terribly important. And it's actually a little bit beyond the scope of this course, but it comes from Kirchhoff's voltage law. Basically, if we consider this loop and apply KVL, if we start here, then the battery, we're crossing from the negative terminal to the positive terminal, so that's going to be a positive contribution right there. The current is flowing this way, and we're going across the resistor in the direction of positive current flow, so that's going to be a negative contribution to delta V. And this is the positive plate of the capacitor because it's the one getting hit by the current first, and this is the negative plate. So we're crossing a capacitor from the positive terminal, from the negative, from the positive terminal to the negative terminal, which is why it's a minus Q over C. And all of that is equal to 0. If we substitute the definition of I as dq dt, then that gives us this differential equation, which we can solve for the same equation that's on our equation sheet. And really, this is all that we need, because we've had all sorts of RC problems at this point, and they ask for all sorts of different things. Some of them ask for currents, others ask for voltages. But the only equation that you really have to know is the one that's provided to you on your equation sheet. It's this one, the charge equation. Everything else comes from this equation. Let's say, for instance, I wanted to find the current in the circuit. Well, to do that, current is just the time derivative of charge. So I can take this equation and taking a derivative, let's see, if I distribute the C times epsilon for the, where epsilon is the, or the squiggly E is the EMF, then this first term just goes away when I take its time derivative, and the second term, the two negatives cancel, and I have epsilon over R, which is a current. In fact, that's my initial current, and that's going to be e to the negative t over RC. And if I wanted the potential difference across the resistor, delta V sub R, that's just Ohm's law. I can always apply Ohm's law to resistors and say that the voltage drop across the resistor is I times R. I already have a function for the current. I just multiply it by resistance. And if I want the potential difference across the capacitor, well, I can just invoke the definition of capacitance. Capacitance is defined to be Q over delta V. So if I rearrange that to solve for V, I'm getting that delta V is equal to Q over C. And I already have an expression for the charge on my capacitor. It's this equation that I started out with. So the voltage across that capacitor is just that charge equation divided by C. So again, the equation that's given on the equation sheet, which is this one right here, I think on the equation sheet it actually says Q final here, or Q initial rather. No, sorry, Q final, which is equal to the charge on the capacitor times the voltage of the battery. That's all you need. Everything else can come from that. Let's see, is that it for charging? Yeah. Any questions so far? People like my heart on my background. Nice. Cool. That's charging RC circuits. Discharging RC circuits, it's pretty much the same thing, except the capacitor starts out initially charged. So initially I do have charge on these plates, and this time I don't have a battery or anything like that that's providing EMF, but I still throw the switch at t equals 0. I close the switch and current starts flowing, and the capacitor starts discharging itself through this resistor. Again, the equation they gave us on the equation sheet was Q of t is equal to Q initial e to the negative t over RC, and that's all we need. Everything else can be derived. If I go through that same mini derivation where I apply Kirchhoff's voltage law, let's say that this is the positive plate of the capacitor, and if I start here and go clockwise, then this is the negative plate, and I'm crossing a capacitor from the negative plate to the positive plate. So that's going to be a positive contribution to delta V. And then I'm crossing a resistor in the direction of positive current flow. So that's going to be a negative contribution to delta V. And again, actually a little bit different for this one, the capacitor is discharging. So the current in the capacitor is going to be negative dq dt. If I substitute wherever I see I in this equation, if I put in negative dq dt, I'm going to get this differential equation this time. And this one's a little bit simpler than before. This one you can actually solve with separation of variables. So I think that's something you learn in calc and not DPQ. But regardless, if you solve this differential equation for q of t, you can get this. That's the equation that's given on the equation sheet, and it's all you need. The reason why it's all you need is because everything else can come from it. If you want the current in the capacitor, or the current in the circuit rather, current is just a time derivative of charge, and it's negative here because the capacitor is losing charge. So I is going to be negative dq dt. If I take a negative derivative, I pull out the factor of 1 over RC, Q initial over 1 over RC. That happens to be what my initial current is always going to be equal to. So this quantity right here is my initial current. If I want the potential difference across the resistor, that just comes from Ohm's law. As always, if I want the voltage on a resistor, I just apply Ohm's law, V equals IR. I have my current expression, I just multiply it by R. And if I want the potential difference across the capacitor, I can just apply the same definition of capacitance. Capacitance is defined to be Q over delta V. So if I solve for delta V, I get Q over C. I have my Q expression, or my Q equation rather. That's what I started out with. I just divide by C. Cool. That should be it for the theory on RC circuits. Any questions? How's my pacing?
I was wondering, for the current as a function of time, could we replace the or the charge over V or the charge over C with just the initial voltage?
Yes, absolutely. Yeah, you're talking about right here.
Yes.
Yeah, Q initial over C, that just happens to be what the voltage across the capacitor is. And initially, the voltage across the capacitor is just my initial voltage in the circuit. That's that same quantity right here. And V over R, that happens to be my initial current. Or V over R, that happens to be a current all the time. When it's my initial current, it's my initial voltage too. Yeah, great question.
Okay, thank you.
Anything else?
The RC in the component or in the exponent is just the magnitude of R and C.
Absolutely, absolutely, yeah. We have some capacitance. It has some value in farads, and we also have a resistor. It also has some value in ohms. It happens to be the case that if I multiply ohms with farads, I get seconds. That's why that value RC is sometimes called the time constant. And that makes sense because I need to be dividing something with units of time, this t right here, by something else with units of time, such that I can exponentiate it. Yeah, great question.
All right, sounds good. Thank you.
Of course. Anything else?
I have a quick question. So when
What's up?
you're calculating that time constant, is it the equivalent resistance and the equivalent capacitance?
Yeah.
Like
So
the
if,
RC is...
yeah, exactly. So if I had a circuit that was more complicated than this, let's say I had a few more resistors in series or in parallel, maybe I could find their equivalent resistance first. And maybe I had a bunch of capacitors here. Maybe they were, in series or in parallel. I would add them according to the rules that Tyler discussed. And I would find an equivalent capacitance and equivalent resistance. That's what I would use in my equations. Great question.
Awesome. Thank you.
Yeah.
And then, so kind of going off that, so the delta V R for this expression, like if you scroll down a little bit longer, one more right there. So is that for a single resistor, like that R value when you multiply I by R, or would that be the equivalent for the circuit?
That would be the equivalent for the circuit, just
Okay.
because in my very first equation that I came up with, I guess technically it would be in this expression I used from KVL, but this resistance refers to the equivalent resistance, and all the math that I did following that was for the equivalent resistance. So yeah, that voltage equation would be referring to the voltage across the equivalent resistance of all the resistors. And we can do more stuff with that hypothetically.
Okay, thank you.
Yeah, of course. Anything else? We're going to move on to topic 2F. Cool. Awesome. We're on the home stretch. We have one last topic, and that's just AC circuits. So an AC signal is a signal that varies with time, as shown below. So it doesn't have to be a sinusoidal function, but that's what we deal with in Phys 2. And that's the most common applications, like in the real world. Like when you stick your phone charger into your wall outlet, the signal coming out of there is an AC signal with 120 hertz and whatever amplitude, I don't know. But what that means is we need two parameters to describe an AC signal. We need its amplitude, and that can be either V naught or I naught, whether you're talking about voltage or current. And we need to know the frequency. And the frequency is just measured in hertz, where 1 hertz is 1/second. So if something happens at a frequency of 1 hertz, that means it happens like once per second. So for instance, for this signal right here, if I zoom in, I think I just straight up plotted a sine function. So this intercept is at pi, and this is at 2 pi. So its frequency would be its frequency would be 1/2 pi. Yeah, because the function I'm plotting right here, I guess I should have labeled it, is I is equal to sine of omega t, and omega is just 1 because the first intercept is at pi. So if I wanted to solve for my frequency, which is like the actual number of times that I see a peak going through the signal, I would use this equation and say that my frequency is 1/2 pi. But that's not too terribly important unless they ask for it. All we have to know is that an AC signal has two parameters, its amplitude and its frequency. The more common thing that you work with, I believe, is omega, which is the angular frequency, just because it's a little bit easier to do math with. Cool. So for AC signals, you need to know, or what we have to work with by virtue of us working with AC signals is root mean square values. So let's suppose I have a current given as I of t is equal to some maximum value times cosine of omega t. Its root mean square value, let's think about what the name implies. Root mean square. I take the square root of the mean of its square value. And what that literally means is I square the signal. So instead of I max cosine of omega t, it's I squared maximum cosine squared of omega t. I take the average of that. And I think, I don't know, Calc 1 or Calc 2, averages was just, we look at some time interval and integrate over that time interval and then divide by the length of that interval to find what the average is. If you do that for a cosine squared value, or if you do that for this function rather, what you're going to get is I squared max divided by 2, and then you get I max over root 2. And this equation is on the equation sheet. And it's true for any sinusoidal function. If I have a quantity that varies as a sinusoidal function, the RMS value is just the maximum value divided by root 2. And that's actually what I have to use in these equations here. So if I have a resistor circuit, just like a AC signal source, and that's going into a resistor, the power dissipated by that resistor, it's no longer I times V, but it's now, the average power is now I RMS times V RMS. Or if I don't want to calculate both the RMS current and the RMS voltage, I can just use the RMS current, square it, and multiply it by the resistance to get the average power. And I can also say that the average voltage across that resistor is equal to the average current or excuse me, the RMS voltage across that current is equal to the RMS current times the resistance. So basically just Ohm's law, except everything now has an RMS in front of it. Any questions there? Yes, please. Could you show the sinusoidal model function again for AC? Yeah. I should have labeled it, and I will when I post these slides, but all this function is it's sine of t, because I have an amplitude of 1, it's a sine function, and just like a regular sine function does, it has a period of 2 pi, because this is 6.28 or something.
So just to clarify quickly, the amplitude is the distance from the x-axis to the peak to one of the peak values, right?
Yep.
Thank you.
Let's see what else. Yeah, if nothing else, I'll move on to whatever's next, which is resistors and AC circuits. Yeah, okay. So if I have the circuit shown here, where I have some input voltage V of t, and let's say it's equal to cosine of omega t, and I'm just sending that through a resistor. Pretty much just as simple of an AC circuit as I could come up with. Ohm's law still holds. I already wrote down what Ohm's law is going to be right here. And if I wanted to find what the current in the circuit is, the current in the circuit is just going to be whatever voltage in the circuit is divided by R. And that voltage function was equal to V naught cosine of omega t. So the current function is going to be V naught over R times cosine of omega t. This quantity V naught over R, that's going to happen to be your amplitude of the current. So that's going to be I naught. Cool. And then for capacitors and AC circuits, yeah, this is something Tyler got asked about. So for the circuit shown with input signal, so it's the same input signal as before. V of t is equal to V naught cosine of omega t. I'm still sending in my input signal right here, except now instead of a resistor here, I have a capacitor. This one's a little bit more tricky. I can't just use the same stuff that I used before for DC signals and capacitors. What I have to do is I have to say that the charge on the capacitor is C times delta V. That just comes from the definition of capacitance. And I know my voltage function is V naught cosine of omega t, so I put that in there. So if I want to find the current in the circuit, well, current is just the time derivative of charge. So I of t is equal to the derivative of this expression up here. C and V naught, those are both constants, so I can pull them out of the integral. And moreover, when I take the derivative, and moreover, when I take the derivative, I have to remember the chain rule factor of omega, that comes out. And here's the really important part, is that the derivative of cosine is sine, negative sine, but that's not. What I'm getting at is that the voltage function is going to be like a cosine function, and then the current in the circuit is going to be delayed. It's going to be shifted out by a phase of 90 degrees, because that's how much cosine differs from sine, by 90 degrees. So that's just something to keep in mind. I don't think we do too much with that in Phys 2, but maybe if you take Mackey circuits or Phys circuits, definitely you'll see that down the road. Yeah, but don't worry too much about that for now. What's more important for us is to quantify things. So if I go back here, I can say that the amplitude of my current function is just I naught. It's whatever factor is in front of the sine function. And that happens to be V naught times omega c. So let's define a quantity x such that this expression kind of looks like Ohm's law, right? Because I have V, now instead of IR, I have XR. But what's this quantity x? Well, x is just whatever I have to multiply I naught by in order to get V naught. And that happens to be 1 over omega c. X is known as reactance, and it sort of plays the role of resistance for a capacitor. So reactance is small for large omega. If I have a large omega right here, reactance is going to be not that big, and it's going to be large for small omega. And this was exactly the question that Tyler got earlier, whether or not capacitors work with AC. Capacitors do work with AC, but this is sort of just a way of quantifying the statement. With low frequency input, capacitors prevent current flow. Because if I have a low frequency signal, then omega, my angular frequency, is going to be really small for a low frequency. Well, if omega is small and I'm dividing by a small number, then the reactance is going to be super duper high, and I'm not going to have that much voltage across my, or excuse me, I'm not going to have that much current in my circuit if I just have a capacitor there. Cool. Don't think I'm forgetting anything. All right, so let's put them both together in a circuit. So now I have not just a resistor, but I also have a capacitor, and I put them together in an AC circuit, sort of looking like this. I still have my same input from before, V of t, except now I have both of these. I can't just straight up add the reactance with the resistance. I can't add X, which I found from here before. I can't add X to R. If I want to quantify how much total effective resistance this circuit provides, that's going to be with a new quantity called impedance. And impedance is defined as the square root of R squared plus X squared, which if I plug in X, that's going to be 1 over, or rather it's going to be R squared plus 1 over omega C squared. And this equation is on your equation sheet. So impedance is just a way of quantifying what the total effective resistance is, because we can't add X and R because they're not in phase. Cool. So if I wanted to find the RMS current through the entire circuit, that would just be with this modified version of Ohm's law. V RMS is equal to I RMS times Z, where V RMS is the input signal, whatever is coming out of here. All right. And low pass filters. Yeah, Tyler, correct me if I'm wrong, but because you started the same time I did, but I've never seen an exam 2 question about low pass or high pass filters. So hopefully this won't be on the test. I just put it here more for reference. I'll just go through it super quickly.
Yeah, Nick, if you're talking about the first month's question, I have never seen it. I would be surprised. But
same
that's not to say.
Same with multiple choice. I don't think I've ever seen one.
Yeah, that's not to say Todd couldn't throw a wrench in it, but I would be surprised.
Yeah, so what I'm trying to say is that it's improbable that filters will be on the test. But regardless, it's here just in case. A low pass filter is when I have an input signal and I'm sending it first through a resistor and then through a capacitor, and I'm measuring the output voltage across the capacitor. Gain is going to be the ratio of the output voltage to the input voltage. The output voltage is just the voltage on the capacitor. The input voltage is the voltage of the whole entire signal, so that's just going to be I times Z, because that's what I defined it here to be earlier when I had both resistors and capacitors. And my output voltage is across the capacitor, so that's going to be I RMS times X. The I's cancel, and I have XC over Z, and I got this equation that we applied in Friday's studio. I'm sorry, Wednesday's studio. Yeah. And same thing, or slightly different thing for high pass filters. All that changes is the placement of the resistor and the capacitor. Now the capacitor is first, and I'm measuring the voltage across the resistor. Same exact formula for gain. It's going to be the ratio of the output RMS voltage to the input RMS voltage. The output RMS voltage is the voltage on the resistor, which is just I times R. The RMS currents cancel, and I get R over Z, which is that. But yeah, like I said, super duper improbable that those will be on the exam. All right, any questions? We can use that expression to find voltage across capacitors in AC. Yeah, so if I just have a straight up a capacitor with nothing else in a circuit, if I just have this circuit by itself, where I have an AC source and a capacitor, if I wanted to find what my current in the circuit is, that is just going to be V is going to be equal to X times I. Yeah. Great question. Anything else? Could you show the sinusoidal model function? Oh yeah, I think I already did that. All right. I think that's about it.
Right on. Good job, Nick. Cool, guys. So sorry we ran a little bit late with content this time. We tried to go a little slower and show more examples in the moment. So we hope you guys found that useful. But that doesn't mean we're not taking off yet. Don't worry. We've still got the ones that you guys voted on. And so it looks like AC circuits, RC circuits, and Kirchhoff's laws had the biggest amount of votes, which is totally fine. We kind of expect that. So each of us will go through one of those examples a piece, and then we'll stick around if you guys have any other remaining questions. But if you guys are taking up, that's totally fine. I'm sending the link again to that exit poll. That'd be great if you guys could fill that out. Like I said, we just don't want to waste your guys' time. So if we have any feedback and things for us that we want to improve for next time, to go ahead and put that in there. But otherwise, Kate, are you ready with a Kirchhoff example, or do you need more time?
Yeah, so I think I'm good to go. I pulled one up from some of the question sets.
Cool. All right.
Yeah.
Yep. So I just tossed that link back in there. Go ahead and feel free to fill that out, guys, when you get a chance. But Kate, sorry, floor is all yours, man.
All right, let me make sure I got this all pulled up. All right. Can everyone see this little notepad that I got going on here?
I can see it, Kate. You're good.
Cool. All right. So one of the questions that it seemed like a lot of people had was how to do all the things that we were talking about whenever we have capacitors in a circuit. And so I went ahead and I found this problem wherever we have things like an EMF source, capacitors and resistors all in one. And what we can kind of go through is talk about it a little bit conceptually, and then we'll go ahead and write down the rules that will apply to the circuit so that we would know how to solve it if we had to, okay? And so the first thing that I want to address is that whenever we're thinking about these circuits, wherever we have both resistors and capacitors, one of the things that happens at the very beginning is how we can model this circuit as soon as this switch is closed. And essentially what you want to think about, and kind of relating this to how current changes with respect to time, what ends up happening is something like that graph that we saw very early on, wherever we have current on this axis, time here, and we see this kind of sloping drop off until we get very, very low, right? And so essentially what this is telling us is that at around time is equivalent to 0, I have a system wherever these capacitors can basically be treated just like wires. I can go ahead and find the total amount of current that's going through this by just evaluating it as if there wasn't any capacitors in it. I can just evaluate it in terms of resistances, and that gives me an accurate depiction to solve how much current is being provided to the circuit. Whereas in opposition to that, and especially in the circuit that I have here, at a very, very long amount of time, I will not have all that much current going through my capacitors, right? As you kind of see, as we progress in time, you get lower and lower amounts of current. So the majority of the current that I will have going through the circuit will then be put into this lower box here that I'm about to put in red, this lower box here, right? Because there's no capacitors that are keeping it from progressing through this portion of my circuit, right? So seen as over time, as charges beginning to accumulate on those capacitors, they kind of act like brakes in the circuit. I can actually just evaluate this smaller portion that only has a resistor after a very long amount of time after the switch S has been closed. So that's a little bit of a conceptual idea of how to approach these, and there may be some questions associated with that. So kind of stemming off that, do we have any questions associated with any of those concepts? All right. And so the other portion that I wanted to do while we were all here together is go ahead and define some of the loop rules, some of the junction rules that we could do for this. So I'm going to go ahead and show this junction right here, the one on the left. And the way that I can just generally write this is that the sum of all of the currents will be equivalent to 0. And this differs a little bit from what we did earlier, because earlier we had guesses as to which one of them, we said that they were all converging on one point, and those guesses could be given by negative values to indicate a difference in direction. But here we actually have the direction of each of the currents indicated. So I know that the way that I've written it currently, I1 would be a positive value, whereas the values of I3 and I2 would be negative because they're flowing away from that junction. Okay, so in all actuality, the value or the magnitude of I2 and I3 will be negative amperes if I were to put this down in like the quantitative units that I would have. And so that is how I can express my junction rule for this. And the same thing is true for the other junction. It's just going to be indicating currents either coming away or towards it in the opposite signs. So I'm going to do a very similar thing to what I did for the very first problem, where I'm going to do these loops in a clockwise manner. And so what I'll do is I'll go ahead and I will start with this top loop, right? So starting from this point here, just above our junction, I'll go ahead and come across my capacitor. And what I've done for you guys to make it a little bit more clear as to what's going on is I've indicated which side is positive and which side is negative. So I know that if I go across this capacitor here at some intermediate time, you know, after the switch has been closed, but not at a point where I don't really have current going through it, what I can say is that I will have a drop in the amount of voltage across V1. And so I'll just indicate that by V subscript C1. And then as I'm following this, I'm going in the direction that current is actually indicated here. So I'm going in the direction of current across a resistor. And so therefore, I will also have a subsequent decrease in voltage indicated by I3R2. And that's just using Ohm's law in order to solve for the voltage drop that I will gain or lose as I go across this. Then we run into our next capacitor, which in this case is also going to be negative. It would be VC2. And coming back around, once again, we're going in the direction of the current. So as I approach, and I'll go ahead and show the current one more time, it's going around in this direction. As I'm going around in the same direction as the current, I will once again have a voltage drop for my second resistor that I've run into here. So that would be indicated by I3R3. And so now to go ahead and close this, I'll come onto this last leg, and I am now going across R1. But the key difference here is that I'm going in the opposite direction as indicated by I2, that current there. So since I'm going in the opposite direction of the current, I will actually have a voltage gain coming across this resistor 1. So that will be indicated by I2 times R1. And then using our Kirchhoff analysis, we know that this will all be equivalent to 0 because this is essentially a conservation of energy equation. And so I know that all of these elements add together should be equivalent to 0 in the end. All right. And so this right here is going to be my top loop equation. Are there any questions about that, or can I get a thumbs up or a got you from Tyler?
Kate, you just got one question in the chat. That's all you got.
Okay, I have to go back and forth in between that and the actual chat on this, so
you're
I
good.
just want
You're
to make
good.
sure. If I was going counterclockwise, would it be negative I2 R3? Saying if I was going the opposite direction of what I'm doing here, would it be negative for R3? Yes, that would be true, because essentially how I'm attributing this is that each of these currents go the entirety of the way until they meet a junction. So I would say that I3 goes across this entire top portion of my circuit and meets down at this junction here on the right. And so if I was going counterclockwise, I would still associate I3 with R3, but it would be positive as I'm going in the opposite direction of that current. Okay, so now the other portion of this, I'll go ahead and do the bottom loop. And this one is much, much simpler. Not very many things included here. And so all that I have to really take into account is going to be my voltage source, that battery that I have here. And this will be my positive terminal. This will be my negative terminal. And in addition to that, I will be going in the direction of current. So as I come across, I will be coming across to the positive side of this battery. So I will say, I'll just do 1, and then I will be coming across in the direction of that current. So I will actually have a voltage drop here. And so that is saying that I2 times R1 should all be equivalent to 0, same thing, but much simpler because I only have a few elements. And so now the final equation that I could define for this, depending on what exactly I was being asked for, comes down to that exterior loop. And really, it's just going to be somewhat of a combination of the two. But the key thing is that I don't have that R1 circuit in there. So same thing that we did earlier, I can just add the two. And what you'll see is that I get an equation that is equivalent to if I just went around and defined each of them again. What will happen is that I'll have a cancellation of my term for I2 R1. And the resulting equation will just be each of those summed, so that I get the EMF associated with this battery, and then subtracting each of my capacitors once again, because as I go clockwise around the external loop, I come out on that negative terminal, and so therefore I'm going to attribute a negative drop in velocity as I go across. And so it's just going to be everything that I have associated with that top loop added on to my voltage source that I had from the bottom. And that is how we would set up our system of equations for a circuit that not only has resistors, but also capacitors and things like that as well. And so it would be the same kind of a general idea if you were asked to solve for something like I3 or any of the associated currents. You would just solve one of these equations in which you have a simpler form for one of the variables and then plug it in. And once again, you can do that with a system of equations, and it does help to simplify it quite a bit whenever you have some system of equation solver, whether you have a TI or anything like that. All right. Are there any kind of conceptual questions about that? I know that some students kind of get tripped up about the fact that we can act as if the capacitors are just wires at time equivalent to 0, but after some amount of time, they kind of act as brakes because they don't allow that current to pass. Any sort of conceptual questions or anything that's not clear? What would we use for the voltages across the capacitors? So I guess that would kind of come down to what the problem statement gives you. If they tell you like a specified voltage with time, you could just use that. But generally what you would want to do is you would be given a capacitance value for that specific capacitor. So like for like C1, we might know that it's something like 10 farads. That's not a reasonable number, but it could be something like 10 farads, right? And so I could solve for the voltage at a given time using the equations that Nick was providing to you, wherever I can solve for essentially the amount of charge Q based off whether it is charging or discharging, and then use simply that equation for here. I'll go ahead and scroll down and write a little bit, wherever we say that C is equivalent to Q over delta V. And so all I would want to do is rearrange that to solve for delta V. And if I knew my charge associated with time, what I could do is just divide that charge associated with time, whether it's charging or discharging, by the capacitance that this element is rated to get my voltage at that time. Does that make sense? All right. I'm glad that clears that up. So the I3 times R2 is negative because the voltage coming off of VC subscript 1 is negative. So you're asking why I3 R2 is negative. So the reason why I3, so essentially this portion, the reason why I was saying that it is negative is because I'm going around in a clockwise fashion, right? That's how I've indicated for each of my circuits and each of my loops, right? And so if I know that current 3 comes out of this portion of the circuit, I'll use pink. So if I know that it's coming out of this portion of the junction and it's coming across each of these, it's progressing around this loop in this way. I know that I am going in the same direction as the current. And whenever I have current in that direction going across a resistor, I get a drop in voltage. That's essentially what you see if you were doing something like measuring voltage on one side of, or sorry, excuse me, if you were measuring across this, you would see that there's a voltage drop. And that's because due to Ohm's law and everything that we're applying here, whenever we get some amount of current going across times the resistance, we have a change. And so therefore, I know that since I'm going in the direction of the current, I should have a drop in voltage going across. So I would say that it's because of my direction of current and the direction of my loop, rather than anything associated with anything upstream like C2. C2 shouldn't really affect the sign or anything associated with R3. The conceptions of how I get those signs and whether it's negative or positive comes from the direction of current and the direction that I'm using my loop to go around the circuit. All right, in that case, for finding charge, is the resistance and capacitance the total for the circuit, or is it just at that point? R and C are always equivalent values. Good question. Okay, that makes more sense. All right, so is there anything remaining from that? I think Tyler answered that last one. So anything else? Are we feeling good with Kirchhoff whenever it's applied to RC circuits? Feel free to say anything, guys. I'm not. And now is the time to unmute.
I think you did good. I think you did good, Kate. I think we got all the questions, unless anybody has any random last ones. But I think that was a great summary. Thanks for bringing up that problem.
All right. Well, I appreciate it, and I'll pass it on to Nick or Tyler, whoever's going to come up next.
Cool. Nick, I'll take it, then I'll leave the floor to you, and then I got to take off. That sound good? Cool. Take that as a yes. All righty, guys. So Kirchhoff's laws was one of the things that we wanted to cover, but also an RC and an AC circuit problem. So I created an RC circuit problem that looks somewhat similar to a homework problem, but it did change in a small way. So we can go ahead and go through this one. So give us a second to copy this down. If you're doing that, that's fine. But basically what I have created for you here is really just a pretty simple RC circuit, right? I've got a battery as my voltage source over here, right? And then I've got two branches of stuff. I got a branch right here that is just a wire, right? And then a branch on this top side here, which is a capacitor and two resistors, right? So pretty typical RC circuit problem. And then I've got all these associated values with voltage and resistance, things like that. Those are just ones I randomly created, so don't go looking for this problem. But first question we want to know, basically, with this whole mess of words here, right? So assuming the switch has been in position B for a very, very long time, right? So really, that's fancy physics talk for T equals infinity, right? Is really what that's saying, right? And then it's moved to position A at time T equals 0. We want to know what the voltage drop across the resistor, which I should probably specify which resistor that is. Resistor, we'll just say R1 for argument's sake. R1 at time equals 2 seconds, right? So like Kay gave a great introduction to, right? Capacitors behave pretty interestingly in circuits, right? Once they are immediately hooked up to a circuit, they act like wires, right? Because they're empty buckets, to go back to our bucket and water analogy, right? They start off completely empty, right? At least that's what we assume for these type of theoretical problems, right? And then as time goes on, they will fill up, right? Becoming more and more like what we call a break in the circuit, right? Or a short circuit, meaning that once they are full, no more current or charge can be passed through them, right? They basically, like I said, act like a giant roadblock in our circuit, right? So they're pretty useless after that, okay? But that's after some amount of time, right? Which we don't exactly know quite yet. But this question is basically asking, okay, well, what voltage do I have on that right-hand side of the circuit after a certain amount of time has passed, right? So what I like to do first, whenever I am faced with an RC circuit problem, is first just to figure out, am I dealing with a charging or a discharging scenario, right? It's a pretty straightforward question, but the equations are very, very different, right, from charging and discharging. And if you use one when you're supposed to use the other, you're not going to get the right answer, right? So Cade talked about it, and I think Nick talked about it as well, right? But for a charging scenario, right, you're going to have V of t equal to, and Nick, I can never remember it either. I can't remember if it says V final, V initial here. I think it's V final. It doesn't really matter. It's just the voltage of the battery, right? Times 1 minus E to the negative t. Is it? Okay. T over RC, right? Where RC is equal to tau, or that time constant, right? Either way, whatever you want to call it, that's totally fine, right? But this is the charging expression. And how we know it's the charging expression is by plugging in time t equals 0 and seeing what value we get, right? So if I plugged in 0 for t right here, right, that would make this entire term equal to 1, right? And then 1 minus 1 obviously is 0, right? And 0 times V final, or 0 times anything, is going to be 0, right? So really what plugging in t equals 0 here told us is that if I plug in a time t equals 0, I'm going to get a voltage value of 0 volts, right? And that's consistent, right, with what we're dealing with here. For charging, right, we know we start as a wire, right? So nothing is stored in it, right? It's like an empty bucket, right? And we know as time goes on, we're going to accumulate some voltage, right? So this must be my charging expression, because I know that my voltage is 0 at time t equals 0, right? So that's how you prove that to yourself if you forget which one's which on the exam, because I know I definitely did. But I was on the other end of the spectrum, right? Discharging expression. It looks very similar, except there is no 1 minus there, right? It is literally just V of t, right, equals V initial times e to the negative t over RC, right? Where RC is equal to that time constant, right? And again, I can use the same strategy here, right? If I forget which one's which, I can plug in t equals 0 here. Right? If I plug in 0 for t, I will get e to whatever e to the 0, right? Or anything to the 0 power is going to be 1, right? And then 1 times V initial is just V initial, right? So this tells me that at the beginning of my discharging process, right, I will have a voltage on my capacitor, which is true, right? After I've left it plugged in for an infinitely long amount of time, it's going to be full of charge, right? So it's going to act like a battery at that point in time. So it will have some voltage value, right? So just a quick little tip there to help you guys figure out which one's charging, which one's discharging, right? Because I know I couldn't remember, right? But then back to my original question, we'll figure out what phase my circuit's actually in. Am I charging it or am I discharging it? All right, so if I go to my diagram, it says that I've been at B for a long, long time, right? And then I'm going to switch to position A, right? So I'm going to move this switch right over here, right, from B to A, right? Meaning I will connect my capacitor to my my battery, right, which will in turn charge the capacitor, right? So I know I'm working with this sucker right here, right? That was a terrible label. That's a little better, right? So I'm working with that expression right there, right? And somebody asked it, very good question. Whenever we're talking about RC here, right, these are always equivalent values, right? So normally when you guys saw this problem in your homework, right, or something similar, you just had one resistor and one capacitor, so you really didn't have anything else to work with, right? But if I'm dealing with, in this case, where I have more than one resistor here, right, R1 and R2, it is always the equivalent resistance, okay? So with that in mind, now that we got all the theory and all that garbage out of the way, right, I can just plug in my values, right? So I will go down here, use my charging expression. So V of t, right? So I'll just say V after, I believe it was 2 seconds that I wanted to know, right, is equal to V final, right? Well, I know where V final is, right, because it's given to me, right? It's the voltage across the battery, right? Because I know after an infinitely long amount of time, my capacitor and my battery will be at the same voltage. Okay, so V final is just VB here, right? E to the negative 2 seconds over R equivalent times C equivalent, right? So I've got two resistors in series here, right? So to find their equivalent value, I'm just going to add them straight up, right? Opposite of capacitors in parallel, right? Resistors in series, just add them straight up, right? Sorry, not opposite of capacitors in parallel, the same as capacitors in parallel, right? I will add them straight up, right? So where this is R EQ and C EQ, right? So R EQ is going to be just R1 plus R2. Right, in this case would have been 75 ohms. Right, and C equivalent is pretty straightforward because I've only got one capacitor, right? So C equivalent is just going to be at 10 microfarads. Right, so all that good stuff, I will plug all that in and I will get some number out of it. I actually didn't do it because it's pretty straightforward calculations, not too much to get incorrect there, right? I would just remember what these subscripts are, right? That's going to be 10 times 10 to the minus 6 farads. All right, that's what the micro is. Okay. So at the end of all that, I would get some number out of it, right? And that would be the voltage drop across resistor R1, right? It would be the same for R1 or R2, but I just decided to specify R1, right? Voltage drop would be the same. All right. That first part of that makes sense to everybody? That sort of situation makes sense, and the difference between charging and discharging, because it's very important to remember the difference between those two. So I just want to clarify any questions before I move on to the second part. Cool. I'll take that resounding silence as a there is no questions. So, all right. So after we got that one, I'm gonna switch it up on you guys a little. Oh, wait, here we go. Question. Chandler says, did you use the discharging equation by accident? Yeah, sorry, I totally did. Thank you. Shocked nobody brought that up until then. V initial. Thanks, Chandler, appreciate it. 1 minus E negative T over C. I always want to go for the discharging one first because it's easier to write. That's my bad. Sorry, guys. Shocked nobody mentioned that sooner. But yes, I would use the charging expression because I know I'm actually charging. So my bad, my bad. All right, any other questions? Thank you for bringing that up, Chandler. I appreciate it.
So if you were asked to find the voltage drop across like the capacitor, or like that voltage drop is the same for the capacitor and both the resistors?
Exactly, right? Because the capacitor, very good question. The capacitor basically controls that entire branch, right? You can think of capacitor as kind of like a floodgate type of thing, right? Nothing, if the capacitor is full, then nothing will get past it, right? But up until that point, the capacitor and both resistors will see pretty much everything is the same, right? Because whatever has to go through the capacitor goes through R1 and R2 as well. Does that answer your question?
Yeah, thank you.
Cool. All right, yeah, very, very good question. The capacitor is basically the determinant of what goes on in that branch, right? So yes, very good question. That voltage would be the same if I asked you for what is the voltage across the capacitor, right? If I said capacitor instead of resistor there, right? Either way would have been the same number. So very good question. All right. So with that being said, I will move on to the second part. So I'm down here at the bottom for you. I'm just trying to make sure we can still see the diagram. So now I'm saying, so now suppose the switch is moved back to position B after a subsequent time has passed such that VB equals VC, right? What I mean by that is the voltage across the battery is equal to the voltage across the capacitor, right? So those are the same, okay? So now, like I said, back to position B. So my switch went straight back down from position A, right? So from right there to back down to here where the picture has it drawn. Okay, and now I want to know what's the charge on the capacitor after t equals 5 seconds, right? So we can go through this using the same strategy, right? Except now I will use the right equation this time, Chandler. Thank you. I will use the discharging equation because my capacitor is now emptying itself, right? If my switch is connected here, that means my battery really doesn't even matter. Right? My battery is no longer a consequence to me, right? I just have this circuit right here, right? My capacitor in series with R1 and R2. All right, but the good thing is my capacitor acts like a battery now that it's all full, and it will just discharge according to this equation right here at the bottom, okay? So with that being said, I will take that equation, discharging, go all the way down here. All right, and I will write the correct one. T, B, make sure this is final. Yeah, or no, that's initial, it's fine. The initial times E to the negative T over RC here. Right, so a lot of you might notice, well, this is a voltage equation. How the hell is this going to get me to charge? Right? And the answer is it won't inherently, right? We got to make some substitutions like Nick was talking about earlier, right? Using our lovely equation C equals Q over V here, right? So with that being said, that is a V, not a U, right? With that being said, I can rearrange this to solve for charge, right? So Q is equal to C times V, right? And I can rearrange the variables that appear here in terms of charge, right? So that's what I'm going to do. I'm going to say that Q of T is equal to C capacitance times my voltage value, right? And that voltage value is still going to be the initial voltage, right? Or the voltage of the battery, right? So VB or VC, however you want to write it, right? Those are all the same values, right? And then E to the negative T over RC, right? Where these two values right here are still equivalent values, right? As soon as it stops lagging, right? Both of those values are still the equivalents. Okay, nothing about that changed. So our equivalent still going to be R1 plus R2, right? Nothing about that changed. And C equivalent obviously remains the same. It's just that one capacitance value, right? So it's going to be C1, which is 10 microfarad. 75 ohms here. Right, so just because my equation changed doesn't mean that the variables in it inherently changed as well, right? I had to make the charge substitution because that's what the question asked me for, right? But R and C remain the exact same, right? It's still equivalent in both cases, right? I just had to change this right here, right, to be C times V, which are things that I know, but really this is still initial charge, right? Q sub I, right? That is an I apologize. Right, so either way I want to look at it, right? The equation just changes based on the variables that we're given and the variables we have to work with. That's all that changed. Right, but to actually solve my problem, I can still plug in 5 seconds here. 5 seconds equal to, right, 10 microfarads times my voltage, which I said I believe I said it was 10 volts, right? Times E to the negative 5 seconds over, let me zoom in a little bit, 75 ohms here times 10 microfarads. Right, and again, I just came up with this problem, so I don't know what the number is off the top of my head, but pretty straightforward calculation there, right? It's pretty hard to sort of mess that up. And the only reason that you would probably mess that up is just because that is a microfarad, right? Again, times 10 to the minus 6 farad, right? So just remember, make sure to look at your subscripts and things like that on the exam, right? Because they will try to change it up on you. Chandler, so you had a question, but you also said never mind. Does that question get answered for you, or did you realize it wasn't useful?
You answered it as I clicked enter.
Cool. Excellent. Thank you. Good. I'm glad. All right. So that will be, like I said, again, some number there, and we will be good to go. That will give me the charge that is in my capacitor at that amount of time, right? Remember, because it is discharging, so that graph will look like Kate was talking about, right? It will look something like that, right? Where I have charge over time, right? Maybe 5 seconds was like here, right? It's going to be some value that's not the maximum and not the minimum. All right, that's pretty much all I had to these problems. And the best thing about these problems is that really we can't really make them that much harder. Right? The general process always remains the same, right? Figure out whether it's charging or discharging, right? Use the correct equation, right? And then just make sure you get your subscripts and everything right. There's not, like I said, there's really just not too many ways we can complicate these for you. The circuit won't usually have more than 2 or 3 elements, right? More than 2 or 3 things for you to worry about, right? And so you can taking the equivalent values pretty straightforward. So you should be fairly good to go. But does that raise any questions? Anybody have any thoughts, questions, concerns about what I went over here? Are we okay?
I had a question. For the first part,
Yeah, go ahead.
For the voltage we found, I was wondering, is that the voltage dropped across the resistors, or do we have to subtract that voltage from the initial voltage of the battery?
Yeah, that's a good question. And so the answer to that, Tristan, is that it just is the voltage drop, right? With this equation, we already took into account the voltage across the battery, right? That's what this sucker is right there, right? So remember, this is this is a charging problem, so it's going to be an exponential growth type problem, right? So after 2 seconds, we are probably about here, right? Something like that, right? Where this is voltage and this is time. Right, so when we solve for this, we don't have to do anything extra, right? It's just the voltage present in or the voltage drop across that resistor at that time, right? That's all there is to it. There's no fancy tricks, anything. That's just the answer. Does that make sense?
Yeah, I just thought that was the voltage dropped across the capacitor at that time, but I guess that also counts for the resistor. So
Yeah, exactly, right? Voltage across the capacitor and the resistor are going to be the exact same, remember, because the capacitor controls what goes through this branch, right? If I've got charges and current coming through that upper branch here, right here, right, they have to go through the capacitor first, right, to get to the both resistors, right? So if I had you solve for the voltage across this resistor right here, right, that's going to be the same as the voltage drop across that and the voltage drop across that. Right, they're going to be the exact same.
okay, all right, thank you.
Yep, sound fair? Cool.
Yep.
All right, yeah, good questions, guys. Very good questions. Anybody have anything else before I pass it off to Nick for AC? I'm shocked there's actually still this many of you around. I appreciate that. It's 27 people. That's crazy. Normally, I would expect single digits by now.
I have a quick question.
Yeah, go ahead.
When we are, obviously, when I'm taking the test, I don't want to have to derive the current and voltage equations. You know what I'm saying? Because you know how on the equation sheet, it only gives us the like charging and uncharging circuit for just the charge function.
Yeah.
So is it a safe rule to say that like the voltage, so let's say it's a charging circuit. The voltage would just be the V initial times 1 minus E to the negative T over RC.
Exactly.
And then the current would just be the initial current times
That
the
is
1
a,
minus
yeah,
E.
that's a very, very good question, Taylor. I know exactly what you're talking about. And the general answer to that is that you can replace these two variables, right? So voltage over time and the voltage in final and initial with any variable that will change as time goes on, right? Except for one caveat, right? So I will say, let me go down here. This is a very, very, very good question, right? So these two are always true for discharge or for charging, right? Equals V times 1 minus E negative T over RC, right? And then the charge one is just like this as well. So Q 1 minus E negative T over RC, right? Even though current does change with time, right? I can't, the current never doesn't follow this charging expression. The current expression is always adhering to the discharging form, right? And the reason for that, right? So current always follows this sucker right here.
It's because the derivative, right?
Partially, yes. That I don't usually think about it like that, but yes, you're right. And the way I think about it is that if it did follow this charging form up here, right, that would mean that at time t equals 0, I have no current, right? Which is obviously not the case, right? Because we know our capacitor acts like a wire at time t equals 0, right? So this value can't ever be 0, right? But if we plug in time t equals 0, we do get a value of 0, right? So that tells us that this equation is not good. We can't use it, right? For current anyway, right? Because I don't have 0 current at time t equals 0, right? That's not how that works, right? I'm going to have some current, but it will always decrease, right? According to that exponential function, according to this function right here. Does that make sense, Chandler?
So just the, sorry, I'm blanking. The current equation is always just kind of inversely related to there's the opposite of the voltage and the charge.
Well,
you know
so not necessarily the opposite, because remember for voltage and charge, we can still have the discharging forms, right? We can still have this one, right? So it's just that the current only follows the discharging one. Right?
Okay, so in both scenarios, it follows that.
Exactly, right? It's always, you always use this equation whenever you're dealing with current, right? Because again, we can't use this hypothetical form because this implies that current is equal to 0 at time t equals 0, which isn't the case all the time.
Okay, awesome. Thank you.
Cool. Yeah, no worries. That's a very, very good question. Very, very good question. It's important to realize that though your equation sheet just has, I believe, the charge one, right? You can replace that with voltage interchangeably, right? So very good question. At this point, I think I've talked quite a bit. So unless anybody has anything else, I will pass it off to Nick and to take off. It sounds like we all good, everybody? Cool. I'll take that.
Thank you, Tyler.
No worries. I'll take that as a resounding yes. So I will stop that.
Are you,
Nick, I'll pass it off to you.
Taylor?
What's that? Sorry.
Are you gonna be hitting out after right now?
Yeah, well, I mean,
no, it's totally fine either way. I just had a logistics question.
No worries. I think I actually am going to take off. Izzy says hi, by the way. She stopped by. So I think I am going to take off. But do you need me for any reason, or are you okay?
No, then is it okay if I send out the video, or do you have anything to add in the email last time?
Oh yeah, no, go right ahead. That's
okay.
all good.
Cool.
Yep, cool. And before I take off, I'm gonna be that guy and toss this exit poll link in here one more time because I know it'll get lost. But appreciate
It's
everybody's
super
time. You guys have a good rest of your night, right?
Thanks, Tyler.
All right, then I will do the third most popular poll, or the question that you wanted to go over, which was the AC circuits. And yeah, let me start screen sharing. I'm gonna do this problem live, so it's more sort of realistic. But where I'm taking it from, it's from the sample exam 2 questions from fall 2017, AC impedance. All right, let's look at it. The diagram below depicts an RC circuit where C equals that, R1 equals that, and R2 equals that. The resistors and capacitors are connected to an AC power supply with a peak voltage of 12 volts and a frequency of 5 hertz. What is the total impedance of the combination of the resistor and the capacitor? All right, well, if we have this setup, we know that AC impedance, that's on our equation sheet, it's Z is equal to R squared plus X squared, where R squared is the total resistance and X squared is the reactance. The resistors are in series, so all I have to do there is just straight up add them, R1 plus R2. And for reactance, that's just 1 over omega C. But if I go back to the problem and I zoom in, I should have done that earlier because it's tiny. Oh, way too far. That's good. We're given a frequency F of 5 hertz. But if I look at the formula for reactance, they want omega here. They want angular frequency. So what I have to do is, before I put that formula in, I have to say my reactance is 1 over 2 pi F times C, just because the way it's written, or rather the problem gave us an F, but the reactance formula is in terms of omega, which is angular frequency. So putting everything together, I get that expression for my impedance. And if I put that over there and zoom out, let's see if I can plug things in and make it work. Desmos, whoops, desmos.com. And let's see, C is equal to 4.55 millifarads. So C is equal to 4.55 times 10 to the negative 3. R1 is equal to 9 and R2 equals 5.5. R2 equals 5.5. And frequency of 5 hertz, 5.00. So then the total impedance is going to be the square root of R1 squared plus R2, sorry, R1 plus R2, because they are in series, all that squared, plus the reactance, which is 1 over 2 pi F times C. So I'm getting that for my impedance. Let's see if it works. That's going to have units of ohms because it's kind of like resistance. And it did not work. Let's see. 12 volts.
You forgot to square the XC value under the square root.
Thank
the
you.
1 over.
Thank you. Awesome. Yeah, appreciate it. Cool. So now we're being told that we're replacing the capacitor with a larger one. And we're asked if the RC current is going to go up, go down, or stay the same. So let's zoom out so we can, or I can show it here. So here's our circuit diagram. And instead of this capacitor, I'm going to be replacing it with something that has a larger capacitance. And if I have a larger capacitance and I look at my formula in the end here, capacitance is on the denominator here. So if I have a larger capacitance, then this quantity in parentheses is actually going to be decreasing, right? Because capacitance is on the bottom. So if I have larger quantity on the bottom, that quantity in parentheses is going to decrease. So I'm not adding as big of a value. So my total impedance is also going to go down. My impedance goes down, and hence my RMS current goes up. Yeah. Yeah.
Is that because RMS current equals voltage over Z? Over the
Exactly.
impedance? Yeah.
Exactly. Yeah. Yeah. Because RMS current is equal to the RMS voltage, which we're not changing. That's our same input voltage divided by the reactance, or excuse me, divided by the impedance. And we already argued that the impedance is going to decrease because my capacitor is bigger. That means this quantity is decreasing. So my Z goes down. If my Z is going down, that's kind of like having a smaller resistor. The current is going to go up. All right. How's that problem look for everyone? Yeah, people are pointing out my mistake. Cool. There's still 18 people here, so I can show one more if everyone's okay with that. Yeah, let's do that. Let me zoom out a tiny bit. And still in the 2017 exam. But the other question that pertained to AC stuff was the simple AC RMS values. Okay. Yeah, the nice thing about AC questions is that they're typically not too terribly difficult. So let's pull this problem up in the slides. And let's do this problem. All right, so let's zoom in also so you can read it. So the voltage supplied by a wall socket varies with time, reversing its polarity with constant frequency. That's basically just saying that the voltage is a sinusoidal function that's coming out of the wall socket. What is the RMS value of the voltage plotted in the graph? So we argued earlier that any function that varies as a sinusoid with time, its RMS value is just going to be its peak value divided by its divided by square root of 2. So yeah, like I said in the slides right here, if I zoom in, the RMS value is going to be the peak voltage value divided by square root of 2. The peak voltage value looks like it's about 170. And 170 divided by the square root of 2 is 170 divided by 1.44. So it's going to go down a tiny bit. I think it's
120.2.
Yeah, 120. Right on. That actually makes sense. That's like a word forward realistic problem because I think American wall sockets are actually at 120 volts. Cool. All right, when a lamp is connected to a wall plug, the resulting circuit can be represented by a simplified AC circuit. The lamp is basically a resistor with an equivalent resistance R equals 120 ohms. What is the RMS value of the current flowing through the circuit? So basically, this is just telling us that now we're plugging in a lamp into the wall plug, and it's pretty much just an AC source with a load, and that load is that resistor of 120 ohms. So that's when the equation V is equal to R times I comes into play, or V equals IR, Ohm's law. And if my RMS input voltage was 120 volts and my resistance is 120 volts, to find current, that's going to be my voltage, my RMS current, sorry, my RMS voltage divided by my RMS resistance. That's going to give me my RMS current. 120 divided by 120 is 1. Sweet. All right. When a lamp is connected to wall plug, same circuit. The lamp is a resistor. What is the average power dissipated in the lamp? Cool. So average power, that is going to be kind of like, let's see, do I have it up here? Nope, I don't want that slide. Give me a second to pull up the other. I keep closing it stupidly. I shouldn't, but you have there we go. Yeah, I keep closing it, but I shouldn't. Where am I looking? Right here on the root mean square page. If I wanted to find the average power on some circuit load, in this case, it's the load being consumed by the lamp, I can just straight up take the RMS current squared and multiply it by the resistance. That's going to give me my average power. It's the same average power I had for DC circuits, but now I just use RMS values. So what I do here, let's close that tab. What I do here is I take my current, my RMS current squared, which 1 squared is 1, and I multiply by my resistance, 120. That's going to give me an average power of 120 watts. How's that all sound for everyone? Let's look at the chat. Yeah, and there's not that many of you left. So at this point, if you just want to speak up, that might be easier than looking in chat, but feel free to do whatever works for you. And stop sharing for now. Yeah, I guess if we want, we can go over I guess the next most popular question in the poll, since there's still a couple of you guys left.
So I don't know about everybody else still here, but for me, I get most confused on AC circuits when you have to do the RMS and you have to do all that junk with the sines and cosines, and somehow they cancel out to the root to over root 2. And I'm just not really sure when I'm supposed to be making that reference, when I can just take the shortcut basically.
How to derive the RMS current expression?
Not necessarily derive it, but how to, like, when to use it basically. Because I know in my discussion we went over a couple problems where he was able to basically he was basically able to skip a lot of the math and result to the value over the square root of 2. And that derivation just somewhat confused me.
I can show you the derivation real quick. People sometimes make it more complicated than it needs to be, if that would help.
Yeah, that would help.
But as far as just using values in your circuit, or rather in your problems, basically the rule of thumb is that whenever you're doing AC stuff, or whenever you're doing anything that pertains to AC circuits, that's when you want to use RMS values. Because if you just try to use peak voltage and peak current to find the power dissipated in an AC circuit, it won't work. But other than that, yeah, I'm trying to think of exceptions to that rule. I can't right now. Yeah, but regardless, here is the derivation of where the square root of 2 comes from. It's right here. So deriving the RMS relationship. Basically, if I just straight up have some signal, like a sine wave, for instance, with amplitude A, or I guess I changed it to V peak, but whatever. It has some amplitude, and I want the root mean square. So if I just think about what that name is, I square it first. So if I square this, I get V peak squared times sine squared of omega t. Then I find its average value, which is just integrating over a period. That's from Calc 2 or Calc 1, I can't remember. But Yeah, average value. I take some function that I want the average value of, and I integrate it over its period. So its period is 2 pi over omega. So that's what I'm integrating over, and then I have to divide by 1 minus 2 pi. Sorry, I have to divide by the length of the period. Yeah, that's it. I have to divide by the length of the period, and the length of the period is 2 pi over omega. So if I'm dividing by that length, I'm essentially multiplying by omega over 2 pi. And I can pull out v peak squared because that's just a constant too. If I square, or if I take this integral, I come up with that. And I get v peak squared over 2. And then finally, I just take the square root. So v RMS is just v peak divided by root 2. The derivation itself is not too terribly important.
So we're never going to be asked to like explain that or do that on an exam, you don't think?
100%. Yeah, that's definitely not going to be asked.
Okay, that's what I was probably most concerned about because I was like, holy crap, I haven't done that math in a while.
Yeah, no, you're good.
Okay, thank you.
Of course. Anything else I can help with for the 6 of you who are still here? Of course. Glad everyone found it useful. Have a good night.
And then there were 2.
And now there's just us. So I'm going to stop
All right.
the
Yeah, stop the recording.